before T-Rex ruled the earth, before the first dinosaur ever drew breath. There was a world so alien, so terrifying, that it would make Jurassic Park look like a petting zoo. Imagine dragonflies the size of eagles, millipedes longer than your car, and predators with jaws that could crush bone. But these weren't dinosaurs. They were something else entirely. This is the story that 300 million years tried to bury. Welcome to the era of giants that time forgot. If you want to journey through Earth's most mind-blowing mysteries, hit that subscribe button and turn on notifications, because what you're about to discover will change how you see our planet's history forever. Imagine standing at the edge of a primordial forest 350 million years ago. The air around you feels different, almost electric. With every breath, your lungs fill with an atmosphere so rich in oxygen that it would make you feel lightheaded, energized, perhaps even intoxicated. This is the Carboniferous period, and you've just stepped into one of Earth's most radical experiments in atmospheric chemistry, a time when the very air itself transformed life into forms so gigantic and alien that they defy our modern imagination. Today, when we breathe, approximately 21% of what enters our lungs is oxygen. It's a balance that has remained relatively stable for millions of years, a sweet spot that supports the incredible diversity of life we see around us. But during the Carboniferous period, that delicate balance was shattered. Oxygen levels soared to an astonishing 35% of the atmosphere, nearly 2/3 higher than what we experience today. To put this in perspective, if you could somehow travel back to this ancient world, every breath would deliver significantly more oxygen to your bloodstream than your body was designed to handle. You would quite literally be breathing supercharged air. But why did this happen? What cosmic accident or evolutionary milestone could have triggered such a dramatic shift in Earth's atmospheric composition? The answer lies in one of the most successful biological innovations in our planet's history: trees. Not just any trees, but the first true forests, vast continental expanses of vegetation that spread across the ancient supercontinent of Pangaea like a green wildfire. These weren't the familiar oaks and maples we know today. These were strange, towering organisms called scale trees, or lepidodendron, some reaching heights of over 100 feet. Their bark covered in a distinctive diamond pattern of leaf scars that made them look more like gigantic pineapples than modern timber. These prehistoric forests were photosynthesis factories on an unprecedented scale. Every single day, billions upon billions of these trees and their companions, the giant ferns and horsetails, absorbed carbon dioxide from the atmosphere and released oxygen as a byproduct. This had been happening for some time in Earth's history, but the Carboniferous period marked a turning point. You see, the organisms responsible for decomposition, the bacteria and fungi that break down dead plant material and release carbon dioxide back into the atmosphere, hadn't yet evolved the ability to efficiently digest lignin and cellulose, the tough compounds that make up wood. So when these massive trees died, they didn't rot away as trees do today. Instead, they fell into the swampy wetlands that dominated the Carboniferous landscape, and were buried, layer upon layer, preserved in oxygen-poor sediments where decomposition ground to a near halt. The carbon they had locked away during their lifetimes stayed locked away, buried deep beneath accumulating layers of peat. Over millions of years, the weight and pressure of these accumulating layers would transform this ancient plant material into something we know very well today: coal. In fact, the name Carboniferous literally means coal-bearing, and the vast coal deposits we've been mining and burning for the past few centuries are the compressed remains of these primordial forests. But while carbon was being sequestered underground, oxygen continued to pour into the atmosphere. Year after year, millennium after millennium, the concentration climbed higher and higher, and as it did, something extraordinary happened. The fundamental rules governing the size and shape of life began to change. In our modern world, insects are limited in size by a critical biological constraint: how they breathe. Unlike mammals with lungs or fish with gills, insects don't have a centralized respiratory system. Instead, they rely on a network of tiny tubes called tracheae that run throughout their bodies, delivering oxygen directly to their cells through passive diffusion. This system works beautifully for small creatures, but it doesn't scale up efficiently. As an insect grows larger, the distance oxygen must travel to reach the innermost cells increases, and diffusion becomes less and less effective. This is why the largest insects today, like the Goliath beetle or the Atlas moth, are still relatively small compared to vertebrate animals. But in a world where oxygen made up 35% of the atmosphere, this equation changed dramatically. With so much more oxygen available in every cubic centimeter of air, diffusion suddenly became far more efficient. Oxygen could travel much further through those tracheal tubes, penetrating deeper into larger bodies. The size ceiling for insects was lifted, and life responded with explosive creativity. The Carboniferous forests buzzed and crawled with creatures that would seem like monsters to our eyes. Dragonflies the size of hawks patrolled the skies, their wingspans stretching up to 2.5 feet across. Millipedes longer than an adult human crawled across the forest floor, their armored segments clicking together as they moved through the undergrowth. Scorpions as large as small. Dogs scuttled through the leaf litter. Even cockroaches grew to proportions that would give any modern exterminator nightmares, some species reaching lengths of several inches. But the impact of this oxygen-rich atmosphere extended far beyond just making things bigger. It transformed entire ecosystems, creating a world that operated under fundamentally different rules than our own. Wildfires, for instance, became far more common and catastrophically more intense. With so much oxygen in the air, vegetation could ignite more easily and burn much hotter. Evidence preserved in the fossil record shows that even wet, living wood could catch fire and burn in this hyperoxic atmosphere. Forest fires would have raged with an intensity we can scarcely imagine, perhaps even creating firestorms that could spread across entire regions, consuming everything in their path before finally running out of fuel. The surplus oxygen also affected metabolism. Creatures living in this environment would have had access to enormous amounts of energy. Aerobic respiration, the process by which cells convert oxygen and nutrients into usable energy, became supercharged. This meant that animals could sustain more intense activity for longer periods. They could grow faster, move more quickly, and maintain higher body temperatures. For predators, this meant enhanced hunting capabilities, For prey, it meant the constant pressure of evading faster, more relentless pursuers. Yet this oxygen paradise was also a double-edged sword. While high oxygen levels enabled gigantism and supercharged metabolism, they also created new dangers. Oxygen is a highly reactive molecule. In excessive concentrations, it can cause oxidative stress, damaging cellular structures and DNA. The creatures of the Carboniferous had to evolve sophisticated biochemical defenses, enhanced antioxidant systems to protect their cells from the very element that made their enormous size possible. The climate during this period was equally extreme and variable. The early Carboniferous enjoyed warm, tropical conditions across much of the globe, with extensive equatorial rainforests that remained wet year-round. These were the swamps where the great coal forests grew, steamy jungles where the humidity hung thick in the supercharged air. But as the period progressed, the climate began to shift. Ice sheets started forming at the South Pole, locked up vast quantities of water, and caused sea levels to fluctuate wildly. Some regions that had been underwater became dry land, while coastal areas were alternatively flooded and exposed as glaciers advanced and retreated. These environmental oscillations created a dynamic, ever-changing world. Species had to adapt quickly or face extinction. The organisms that thrived were those flexible enough to handle changing conditions, those that could exploit new opportunities as ecosystems shifted and reformed. This was a crucible of evolution, a testing ground where life experimented with new forms and strategies at a pace rarely matched in Earth's history. The legacy of the Carboniferous period extends far beyond the fossil record. Those ancient forests, buried and compressed over hundreds of millions of years, became the coal that powered the Industrial Revolution and continues to generate electricity for billions of people today. When we burn coal, we're releasing carbon that was captured from the atmosphere during this distant age. Carbon that those towering scale trees pulled from the air breath by breath, tree by tree, over millions of years. We're also releasing energy from an atmosphere that no longer exists, experiencing a distant echo of that oxygen-rich world in the form of heat and power. Understanding the Carboniferous period forces us to confront a profound truth about our planet. Earth's atmosphere is not a fixed, unchanging backdrop. It's a dynamic, living system, shaped by the organisms that inhabit it. The oxygen we breathe today exists because of photosynthetic life, from ancient cyanobacteria to modern rainforests. The Carboniferous shows us what happens when that system is pushed to extremes, when feedback loops amplify changes and create conditions radically different from what came before or after. As we stand here in the present, breathing our 21% oxygen atmosphere, it's humbling to realize that we're living in just one snapshot of Earth's atmospheric history. The Carboniferous reminds us that our planet has experienced dramatic transformations before, and will undoubtedly experience them again. It challenges us to think about our own impact on atmospheric composition as we release carbon back into the air and alter the delicate balance that makes our modern world possible. This was Earth's oxygen experiment, a time when the planet tested the limits of how much of this vital element the atmosphere could hold, and what forms of life such conditions could produce. The results were spectacular, terrifying, and utterly unlike anything in our experience. It was a world of giants, a hyperoxic greenhouse where evolution ran wild and created monsters that time has nearly forgotten. Close your eyes and imagine walking through a Carboniferous forest at twilight. The air is thick and heavy, saturated with moisture, and that intoxicating surplus of oxygen. Giant ferns tower above you, their fronds creating a canopy that filters the fading light into a greenish gloom. The ground beneath your feet is soft and spongy, covered in a thick mat of decaying plant material and moss. And then you hear it, a sound that sends a primal shiver down your spine, a rhythmic clicking, like armored plates sliding against one another, accompanied by a wet, squelching sound of something massive moving through the undergrowth. The sound grows louder, closer, and then you see it emerging from behind a massive scaled tree trunk. Arthropleura, the undisputed titan of the invertebrate world, the largest land-dwelling arthropod that has ever existed on planet Earth. What crawls into view before you defies every expectation you might have about the size and scale of creatures without backbones. This is no ordinary millipede you could cup in your hand or watch curl into a defensive spiral on your palm. This is a monster, a creature that stretches 8.5 feet from its segmented head to the tip of its armored tail. To put that in perspective, imagine a millipede as long as a compact car, as wide as your torso, and weighing potentially up to 100 pounds or more. If you were to lie down on the ground, this creature would extend well beyond your height, its body composed of approximately 30 segmented plates, each one overlapping the next, like the armor of some ancient warrior. The exoskeleton that covers every inch of Arthropleura body is a masterpiece of natural engineering. Made from chitin reinforced with calcium carbonate, it forms a defensive barrier that few predators of the time could hope to penetrate. Each segment is a curved plate, slightly wider than it is long, creating a flexible yet incredibly tough exterior that can withstand tremendous punishment. The surface has a slight sheen to it, reflecting the filtered light of the forest in ways that make the creature seem almost metallic, like a living tank forged from bronze and shadow. Running along the sides of this magnificent beast are the legs, dozens upon dozens of them, each pair attached to a body segment. Unlike the delicate, almost fragile legs of modern millipedes, these limbs are robust and powerful, each one thick as a human finger, covered in the same chitinous armor as the body. They move in waves, creating a mesmerizing, rippling motion that propels the creature forward with surprising speed and grace. When Arthropleura walks, those legs create a distinctive sound, a rhythmic tapping and clicking that echoes through the forest like some kind of organic percussion instrument. In the quiet of the prehistoric swamp, this sound would have been unmistakable, a warning to anything in the vicinity that something enormous was on the move. But here's where the story of Arthropleura takes a fascinating turn, one that challenges our instinctive fear of such a massive, armored creature. Despite its intimidating size and tank-like appearance, Arthropleura was a vegetarian. Yes, you heard that correctly. The largest land invertebrate ever to exist was a peaceful herbivore, content to browse on the abundant plant life of the Carboniferous forests. Its mouth was equipped not with fearsome fangs or crushing mandibles designed to tear flesh, but with relatively simple mouthparts adapted for grinding and processing plant material. Imagine this colossal arthropod making its way through the undergrowth, its antennae waving gently as it searches for food. It approaches a stand of primitive ferns, their fronds hanging low and heavy with moisture. The creature's mouthparts engage, methodically working through tea. He plant tissue, stripping leaves from stems with mechanical efficiency. It moves from plant to plant, consuming enormous quantities of vegetation to fuel its massive body. Given its size, an adult Arthropleura would have needed to eat constantly, spending most of its waking hours in pursuit of the calories necessary to sustain such bulk. The fossil record tells us that Arthropleura lived during the late Carboniferous period, approximately 300 to 320 million years ago, making it a contemporary of those oxygen-rich forests we discussed earlier. In fact, Arthropleura's gigantic size was a direct result of that hyperoxic atmosphere. Like other giant arthropods of its time, it breathed through a series of pores along its body segments, relying on diffusion to deliver oxygen to its tissues. In our modern atmosphere with only 21% oxygen, a creature of this size simply couldn't exist. Its respiratory system would fail, unable to deliver sufficient oxygen to sustain such a large body. But in the Carboniferous, with oxygen levels at 35%, diffusion became efficient enough to support this remarkable evolutionary experiment in gigantism. The habitat of Arthropleura was primarily the vast coal swamps and humid forests that dominated the equatorial regions during this period. These environments provided everything this massive herbivore needed: abundant food in the form of ferns, horsetails, and other primitive plants, high humi, diddy, that prevented its exoskeleton from drying out, and a complex landscape of fallen logs, dense undergrowth, and shallow pools where it could navigate and find shelter. Trackways preserved in ancient rocks show us that Arthropleura was likely a lowland creature, preferring areas near water where vegetation grew most abundantly. What's particularly intriguing about these fossilized trackways is what they reveal about Arthropleura's behavior and movement patterns. The tracks show a creature that moved with purpose and surprising agility for something so large. Some trackways indicate that Arthropleura could navigate complex terrain, climbing over obstacles and making its way through dense vegetation. The spacing of the footprints suggests that it could move at varying speeds, from a slow, methodical pace, while feeding to faster movement when traveling between feeding sites, or perhaps fleeing from danger. And make no mistake, despite its armored exterior and impressive size, Arthropleura did face threats. The Carboniferous forests were home to large amphibian predators, some reaching lengths of 6 feet or more, with powerful jaws lined with sharp teeth. While adult Arthropleura were probably too large and too well defended to be regular prey, younger, smaller individuals would have been vulnerable. This may explain why Arthropleura evolved such formidable armor. Each segment of that exoskeleton could overlap with its neighbors, allowing the creature to curl up into a defensive V posture protecting its softer underside and presenting an attacker with nothing but impenetrable armor. One of the most frustrating aspects of studying Arthropleura is how rare complete fossils are. The vast majority of what we know about this creature comes from fragmentary remains, individual segments of exoskeleton, or those precious trackways preserved in ancient sediments. Complete specimens are extraordinarily rare, and for good reason. After death, Arthropleura's segmented exoskeleton would have quickly fallen apart as the soft tissues holding it together decomposed. The individual plates would scatter, making it incredibly difficult to find an intact specimen. However, in 2003, paleontologists in Germany discovered one of the most complete Arthropleura fossils ever found. A specimen that measured over 6 feet long and provided unprecedented detail about the creature's anatomy. This discovery confirmed many hypotheses about its structure and revealed new details about its body plan. More recently, in 2021, a fossilized Arthropleura segment was discovered on a beach in Northumberland, England. This fragment, about 2.5 feet long, came from an individual that would have measured approximately 8.5 feet in total length, making it one of the largest specimens ever recorded. Living alongside Arthropleura in these ancient forests was like inhabiting a world where the normal rules of scale had been suspended. Imagine a juvenile specimen, perhaps only 3 or 4 feet long, still growing into its ultimate size. It crawls through a patch of giant club mosses, their spores drifting down through the oxygen-rich air like snow. Overhead, a massive dragonfly, Meganeura, patrols the canopy with a wingspan wider than a hawk. In a nearby pool, giant amphibians lurk beneath the murky water. Everything is outsized, exaggerated, pushed to extremes by the atmospheric conditions that make such gigantism possible. What did Arthropleura sound like as it moved through this landscape? We can make educated guesses based on its anatomy and the environment it inhabited. The clicking of its armored segments would have been constant, a rattling symphony produced by dozens of chitinous plates sliding against one another with each undulating movement. Its many legs, striking the ground in rapid succession, would have created a distinctive pattering sound, faster and lighter than you might expect from such a massive creature. When moving through water or across wet ground, there would have been splashing and squelching sounds. And perhaps, like modern millipedes, Arthropleura could produce defensive chemicals when threatened, substances that might have hissed or bubbled as they were secreted from glands along its body. Modern millipedes are known for their defensive chemical warfare. Many species can produce toxic or irritating compounds including hydrogen cyanide, benzoquinones, and other unpleasant substances that eater predators. Did Arthropleura possess similar capabilities? We can't know for certain, as soft tissues rarely fossilize, but it seems likely that a creature this size, living in an ecosystem with large predators, would have evolved chemical defenses to supplement its physical armor. Imagine accidentally threatening an 8-foot-long Arthropleura and having it release a cloud of noxious chemicals in response. That would certainly be an effective deterrent. The extinction of Arthropleura remains somewhat mysterious. These creatures thrived for approximately 20 million years, an impressive run by any measure, but they disappeared from the fossil record at the end of the Carboniferous period. The most likely explanation relates to the changing atmospheric conditions, as oxygen levels began to decline from their Carboniferous peak. The physiological advantage that allowed arthropods to grow so large began to disappear. Additionally, the climate was becoming cooler and drier, and the vast coal swamp forests that had provided Arthropleura's habitat were shrinking. The age of amphibians was giving way to the age of reptiles, and new predators with new hunting strategies were emerging. Today, the largest land-dwelling millipede is the African giant black millipede, which can reach lengths of about 15 inches. Impressive by modern standards, certainly, but utterly dwarfed by its ancient relative. When you see a millipede curled up on the forest floor today, you're looking at a distant descendant of Arthropleura, a creature that has been scaled down by hundreds of millions of years of atmospheric and evolutionary change. Yet even in its diminished modern form, the millipede still carries echoes of that ancient giant. The same segmented body plan, the same wave-like locomotion, the same vegetarian lifestyle, the same chemical defenses. Arthropleura may be gone, but its legacy lives on in every millipede that crawls across the earth today. A reminder that our planet once hosted giants beyond our wildest imagination. Picture yourself standing in that same Carboniferous swamp, the humidity wrapping around you like a wet blanket, the air so thick with oxygen it almost feels like you could drink it. You've just watched an enormous Arthropleura disappear into the undergrowth, its armored segments clicking into the distance. The forest around you hums with insect life, a constant drone of wings and chirping that fills every corner of this primordial world. You tilt your head back to look up through the canopy of giant ferns and scale trees, watching shafts of golden sunlight pierce through the prehistoric foliage. And then, something blocks out the sun. A shadow passes over you, swift and silent, far too large to be any insect you've ever known. Your eyes track the movement, and your breath catches in your throat. Soaring through the canopy with lethal grace is a creature that seems ripped from the pages of a fantasy novel. Its 4 wings, each one transparent and veined like stained glass, catch the light and shimmer with iridescent colors. But it's the size that makes your mind rebel against what you're seeing. From wingtip to wingtip, this dragonfly measures over 2.5 feet across, with a body as thick as your wrist and nearly as long as your arm. This is Meganeura, the undisputed master of the Carboniferous skies, the largest flying insect that has ever existed, and one of the most efficient predators ever to take to the air, Meganeura monyi. To give it its full scientific name, was not merely a scaled-up version of the delicate dragonflies that hover over modern ponds and streams. This was an apex predator, an aerial hunter so perfectly adapted to its role that it dominated the skies of the late Carboniferous period, with virtually no competition. Every aspect of its anatomy was optimized for one purpose: hunting and killing other flying creatures with ruthless efficiency. Let's start with those magnificent wings, because they represent one of the most sophisticated pieces of biological engineering the insect world has ever produced. Each of Meganeura's 4 wings operated independently, giving it flight capabilities that modern helicopters can only dream of achieving. The wings themselves were constructed from a thin, flexible membrane supported by an intricate network of veins that created a structure both incredibly strong and remarkably lightweight. These weren't just simple flaps for generating lift. The VI N pattern created corrugations and curves that improved aerodynamic efficiency, allowing Meganeura to generate tremendous power while maintaining the ability to make split-second adjustments to its flight path. Watch as a Meganeura hunts, and you witness a masterclass in aerial combat. It hovers motionless above the forest canopy, its wings beating so rapidly they're almost invisible, creating a low humming sound that would serve as the last warning many of its prey would ever hear. Its enormous compound eyes, each one composed of thousands of individual lenses, provide nearly 360-degree vision. These eyes can detect the slightest movement, can track multiple targets simultaneously, and can calculate speed, distance, and trajectory with computer-like precision. In the high-oxygen atmosphere of the Carboniferous, Meganeura's brain receives so much oxygen that its neural processing operates at peak efficiency, allowing it to make decisions and react to stimuli in fractions of a second. Something moves below, another flying insect, perhaps a primitive flying cockroach or a smaller species of ancient dragonfly. It makes the fatal mistake of venturing into Meganeura's hunting territory. The predator's head swivels, tracking the prey. Those massive eyes lock on, and then Meganeura strikes. The acceleration is explosive. In an instant, the hovering predator becomes a missile, its wings shifting their angle of attack to convert from hovering mode to full-speed pursuit. It cuts through the air with shocking velocity, the aerodynamic design of its body minimizing drag. The prey, sensing danger, attempts evasive maneuvers, banking hard to the left, then diving toward the relative safety of the undergrowth. But Meganeura is already compensating, its independently operating wings making constant micro-adjustments, its brain calculating intercept angles automatically, instinctively. This is what 300 million years of evolution has created, a hunting machine with reflexes honed to perfection. The chase lasts only seconds. Meganeura closes the distance with terrifying speed, and then those legs, armed with rows of sharp spines, shoot forward. The front two pairs of legs form a basket, a trap that snaps shut around the fleeing prey with mechanical precision. The victim is caught mid-flight, plucked from the air as casually as you might catch a ball. But this game has only one outcome. Now comes the truly horrifying part. Meganeura's head is dominated by massive mandibles, jaw structures that look like something from an alien nightmare. These aren't the simple chewing mouthparts of a herbivore or the delicate proboscis of a butterfly. These are weapons, sharp and powerful enough to slice through the tough exoskeletons of other insects with ease. As the captured prey struggles in vain against the spined leg basket, Meganeura's mandibles go to work with brutal efficiency. They shear through chitin tissue, dismembering the victim piece by piece. There's no venom, no merciful quick death. Just raw mechanical destruction as the predator consumes its meal, often while still in flight, the inedible pieces dropping away to the forest floor below. Scientists estimate that Meganeura would have needed to consume a significant amount of food daily to fuel its energy-intensive lifestyle. Flight especially the kind of high-performance aerobatics required for hunting, is one of the most metabolically expensive activities in the animal kingdom. In the oxygen-rich Carboniferous atmosphere, Meganeura's metabolism would have been supercharged, burning through calories at a prodigious rate. This meant constant hunting, constant vigilance, constant violence. The skies of the Carboniferous were a battleground, and Meganeura was the undisputed champion. But Meganeura wasn't just a mindless killing machine. Evidence suggests these creatures possessed sophisticated behaviors that went beyond simple predation. Their large brains, relatively speaking, would have been capable of learning and memory. They could likely recognize productive hunting territories and return to them repeatedly. They may have been able to distinguish between different types of prey and adjust their hunting strategies accordingly. Some paleontologists speculate that Meganeura might have engaged in complex mating rituals, perhaps aerial displays similar to those performed by modern dragonflies, but on a far more spectacular scale. Imagine two of these giants spiraling through the air together, their wings catching the sunlight, performing an ancient dance that predates the dinosaurs by millions of years. The life cycle of Meganeura would have been similar to that of modern dragonflies, beginning in the water. Adult females would have laid their eggs in the prehistoric swamps and pools that dotted the Carboniferous landscape. These eggs would hatch into aquatic nymphs. And here's where things get truly fascinating. Dragonfly nymphs today are voracious predators in their own right, hunting everything from other insect, larvae, to small fish and tadpoles. A Meganeura nymph, proportionally larger, and living in an oxygen-rich environment, would have been a terror of the Carboniferous waterways. These nymphs possessed an extendable lower jaw called a labium, which could shoot forward to grab prey in a fraction of a second. Imagine an aquatic predator the size of a lobster, lurking in the murky waters of a coal swamp, its massive eyes scanning for movement. Small fish, primitive amphibians, other insect larvae, anything that ventured too close would have been fair game. The nymph stage could have lasted for several years, during which the creature would molt repeatedly, growing larger with each transformation. And then, when conditions were right, when its body had reached full size and maturity, the nymph would crawl out of the water, find a suitable perch on a fern stem or scale tree trunk, and undergo its final transformation, the metamorphosis from aquatic nymph to aerial predator is one of nature's most dramatic transformations. The nymph's exoskeleton would split down the back, and slowly, over the course of hours, the adult Meganeura would emerge. Its wings, compressed and folded within the nymphal case, would expand and harden as hemolymph, the insect equivalent of blood, was pumped through the veins. During this vulnerable period, the emerging adult would be defenseless, its soft new exoskeleton not yet hardened, its wings not yet capable of flight. It would cling to its perch, exposed to any predator that happened upon it. But once the transformation was complete, once those magnificent wings had dried and hardened and the exoskeleton had achieved its full strength, a new hunter would take to the skies. The hunting grounds of Meganeura were the canopy layers and open spaces above the Carboniferous forests. Unlike the dense undergrowth where Arthropleura foraged, this was a three-dimensional battlefield where speed, agility, and precision were everything. Meganeura shared these skies with a diverse array of other flying insects, many of which served as prey but also with competitors and potential threats. Other species of giant dragonflies existed during this period, some nearly as large as Meganeura itself. Territorial disputes between these apex predators must have been spectacular affairs. Aerial combat between insects the size of hawks, each trying to drive the other from prime hunting territory. Scientists have long debated exactly how Meganeura achieved such enormous size. The high oxygen content of the Carboniferous atmosphere is clearly part of the answer. As we discussed with Arthropleura, insects breathe through a system of tubes called tracheae, and the efficiency of this system depends on the concentration of oxygen in the air. More oxygen means these tubes can serve larger bodies more effectively. But there's more to the story than just oxygen levels. Recent research has suggested that the lack of aerial predators also played a crucial role. In our modern world, birds dominate the skies and feed heavily on flying insects. This creates strong selective pressure for insects to remain small and maneuverable enough to evade these predators. But birds wouldn't evolve for another 100 million years. During the Carboniferous, the skies were an empty niche waiting to be filled, and insects like Meganeura filled it spectacularly. Without the threat of avian predators, there was no penalty for growing large, and significant advantages in terms of accessing prey and dominating territory. The fossil record of Meganeura is frustratingly sparse, as is often the case with flying insects. Their delicate bodies and thin wings rarely preserve well. Most of what we know comes from wing fragments and occasional body segments found in ancient coal deposits. However, in 1880, a beautiful fossil specimen was discovered in France, preserved in remarkable detail in a layer of fine-grained rock. This specimen, measuring about 70 centimeters in wingspan, became the holotype, the reference specimen for Meganeura monyi. It showed not just the wings but portions of the body, providing crucial information about the creature's anatomy and confirming its massive size. The dominance of Meganeura and its relatives couldn't last forever. As the Carboniferous period gave way to the Permian, oxygen levels began to decline from their historic peak. The vast coal swamps started to dry up as the climate changed and continental drift altered weather patterns. The prey base shifted, and new predators emerged. Eventually, by the end of the Permian period, the age of giant insects was drawing to a close. The ecological and atmospheric conditions that had allowed creatures like Meganeura to thrive were disappearing, and with them went these magnificent aerial predators. Today, the largest dragonflies have wingspans measuring only about 7 inches, impressive by modern standards, but pygmies compared to their Carboniferous ancestors. When you see a dragonfly hovering over a pond, watching it snatch mosquitoes from the air with those same spined legs, processing its prey with those same sharp mandibles, you're witnessing a direct link to Meganeura. The hunting strategies, the flight mechanics, the predatory instincts, all of these have been preserved across 300 million years of evolution. The dragonflies of today are living fossils in a sense, carrying within them the genetic legacy of the terror of the Carboniferous skies. scaled down to fit a world with less oxygen and more competition, but still recognizable as the descendants of giants. Now that you've met the inhabitants of the Carboniferous world, the armored Arthropleura crawling through the undergrowth and Meganeura patrolling the skies above, it's time to explore the stage upon which this ancient drama unfolded. Because the true architect of the Carboniferous period wasn't any animal, no matter how impressive. It was the forests themselves, vast living systems that stretched across entire continents and transformed not just the landscape, but the very composition of Earth's atmosphere, and the future of human civilization millions of years before humans even existed. Stand with me at the edge of one of these primordial forests, and let your eyes adjust to what you're seeing, because your brain will struggle to categorize this landscape. Everything about it feels wrong, alien, like you've stepped through a portal onto another planet rather than simply traveling back in time. The trees that dominate this forest don't look like trees at all, at least not in any way you'd recognize. There are no broad leafy canopies, no spreading branches reaching toward the sun, no thick trunks covered in rough bark. Instead, the landscape is filled with what can only be described as enormous green poles, massive columns that shoot straight up toward the sky with barely any taper, rising 60, 80, even 100 feet into the air before terminating in a crown of leaves that looks more like an explosion than a traditional treetop. These are the scale trees, members of the genus Lepidodendron, and they are the undisputed giants of the Carboniferous landscape. Up close, they're even stranger than they appear from a distance. The trunk isn't covered in bark the way a modern oak or pine would be. Instead, the entire surface is textured with a distinctive diamond-shaped pattern. Thousands upon thousands of leaf scars arranged in spiraling rows that wrap around the column from bottom to top. Each diamond-shaped scar marks where a leaf once grew before falling away as the tree grew taller. The effect is both beautiful and unsettling, like the tree has been carved with geometric precision by some obsessive artist, or wrapped in the scales of an enormous reptile. Run your hand along one of these trunks and you'd discover another shocking truth. The outer layer is surprisingly thin and soft, more like thick cork than solid wood. Cut into a scale tree, and you'd find that the interior is mostly hollow or filled with soft pith. These trees didn't grow the way modern trees do, adding ring after ring of dense wood year after year. Instead, they grew rapidly, shooting upward with remarkable speed, their structure more similar to a modern palm tree than an oak. This strategy allowed them to reach tremendous heights quickly, but it also meant they were relative. Fragile. A strong storm could topple dozens of these giants, sending them crashing into the swampy ground where they'd be quickly buried in the oxygen-poor mud. The crown of a mature lepidodendron was equally bizarre. Rather than branches spreading out in all directions, the tree produced a relatively small number of forking divisions at the very top, each one terminating in a cluster of long, grass-like leaves. From below, looking up through the canopy, you'd see these crowns scattered across the sky like strange green fireworks frozen in mid-explosion. The leaves themselves were simple structures, long and narrow, lacking the complex venation of modern tree leaves. They grew densely packed at the branch tips, and when they died and fell, they left behind those distinctive diamond scars that covered the trunk, But Lepidodendron wasn't alone in this strange forest. Growing alongside the scale trees were their relatives, members of the genus Sigillaria, which grew in a similar fashion but with a slightly different pattern of leaf scars, creating vertical rows rather than spiraling diamonds. Then there were the giant horsetails, relatives of the small segmented plants you might find growing along modern roadsides, but scaled up to heights of 30 feet or more. These plants grew in dense stands in the wettest areas, their hollow, jointed stems rising from extensive underground root systems. And everywhere, carpeting the ground and filling every available niche, were the ferns. Not the delicate woodland ferns of today, but massive tree ferns with trunks thick as telephone poles and fronds that spread out 15 feet in every direction. These tree ferns created a middle canopy layer, filling the space between the forest floor and the crowns of the scale trees above. Their fronds were so large and so numerous that they blocked out much of the sunlight, creating a dim, green-tinted twilight world beneath the canopy even at midday. Walking through one of these forests would have been an exercise in navigating obstacles. The ground wasn't solid earth, but rather a thick, spongy mat of partially decayed plant material mixed with mud and standing water. Your feet would sink with every step, and the smell of decomposition would hang heavy in the humid air. Fallen scale trees lay everywhere, their hollow trunks serving as bridges over pools of stagnant water, or slowly sinking into the muck. The water table was so high in these environments that much of the forest existed in a perpetual state of flooding, with pools and channels connecting different areas, creating a landscape that was neither fully terrestrial nor fully aquatic, but something in between. The sheer productivity of these forests is almost impossible to comprehend. Modern tropical rainforests are among the most productive ecosystems on Earth, but the Carboniferous coal forests may have exceeded even them. With atmospheric carbon dioxide levels higher than today, and that excess oxygen fuel. In rapid metabolism, photosynthesis occurred at tremendous rates. The scale trees in particular grew with astonishing speed. Some scientists estimate that a lepidodendron could grow from a spore to a full-sized tree, 100 feet tall, in just 10 to 15 years. This is blazingly fast compared to modern trees, which might take a century or more to reach similar heights. But here's where the story takes its most consequential turn, the twist that would echo through geological time and eventually power human civilization. When these trees died, and they died constantly, falling in storms or simply reaching the end of their rapid life cycles, they didn't decompose the way dead trees do today. Remember, we're in an era before fungi and bacteria had fully evolved the ability to break down lignin and cellulose, the tough compounds that make up wood. These crucial decomposers existed, but they were primitive, inefficient, struggling to process the massive quantities of dead plant material that accumulated in the swamps. So the trees fell, and they stayed. They sank into the oxygen-poor water, where the lack of air prevented what little decomposition might have occurred. Layer upon layer, they accumulated. A scale tree that had taken 15 years to grow might lie in the swamp mud for thousands of years, barely decaying, slowly being buried by more fallen trees, by fern fronds and horsetail stems, by the constant rain of plant debris from the living forest above. The weight of accumulating material compressed the layers beneath, squeezing out water, increasing pressure, beginning a transformation that would take millions of years to complete. What started as a jumbled mass of plant material became peat, that dark brown, spongy substance that forms in modern bogs, but on a scale dwarfing anything we see today. Some of these peat deposits grew hundreds of feet thick, representing thousands of years of continuous accumulation. And then, as geological time marched on, as continents shifted and seas advanced and retreated, these peat deposits were buried even deeper. Layers of sediment, sometimes miles thick, piled on top. The pressure increased exponentially, the temperature rose, and slowly, inexorably, the peat transformed. First, it became lignite, a soft brownish coal that still retains some of the structure of the original plant material. With more time, more pressure, more heat, lignite became bituminous coal, harder and blacker, with higher carbon content and more energy density. In some locations, where the conditions were most extreme, the transformation continued even further, creating anthracite, the hardest and most carbon-rich form of coal, which burns with intense heat and minimal smoke. This process, this burial and transformation of Carboniferous forests, created the vast majority of Earth's coal deposits. When we talk about coal seams, we're talking about compressed, transformed layers of these ancient scale tree forests. A coal seam, 6 feet thick, might represent a peat layer 60 feet thick, which in turn represents thousands of years of forest growth and accumulation. The coal that powered the Industrial Revolution, that generates electricity today, that built the modern world, is quite literally the compressed remains of lepidodendron and sigillaria, of tree ferns and giant horsetails, all preserved from a time when atmospheric conditions created forests unlike anything seen before or since. Consider the implications of this for a moment. Every lump of coal ever mined, every ton ever burned, represents ancient sunlight captured by these bizarre forests 300 million years ago. The carbon in that coal was pulled from the Carboniferous atmosphere by the photosynthesis of scale trees, stored in their trunks and leaves, and then locked underground for hundreds of millions of years. When we burn coal today, we're releasing that ancient carbon back into the atmosphere, reversing in decades a process that took millions of years to complete. The geography of coal deposits around the world maps directly to where these Carboniferous forests grew. The coal fields of Appalachia in the United States, the massive deposits in China, the coal seams of Britain and Germany and Poland. All of these formed in the vast equatorial swamps that girdled the ancient supercontinent. If you could overlay a map of Carboniferous forests onto a modern map of coal deposits, they would match with eerie precision. But these forests did more than just create coal. They fundamentally altered Earth's atmosphere in ways that would shape the entire future of life on our planet. By pulling carbon dioxide from the air and locking it underground, the Carboniferous forest triggered a dramatic drop in atmospheric CO2 levels. This, combined with the position of continents and ocean currents, helped trigger an ice age that would persist on and off for millions of years. Glaciers advanced across the southern supercontinent of Gondwana. Sea levels fell and rose repeatedly as ice sheets grew and melted. The climate became more variable, more seasonal, creating selective pressures that would drive evolution in new directions. The forests also, as we've discussed, were responsible for that dramatic spike in oxygen levels that enabled the evolution of giant insects and other massive arthropods. Every tree growing, every fern frond unfurling, every horsetail stem rising from the mud was a tiny oxygen factory. Collectively, across millions of square miles of swamp forest, they transformed the atmosphere into that hyperoxic state that made the world of Arthropleura and Meganeura possible. Eventually, of course, the age of these strange forests came to an end. As the Carboniferous gave way to the Permian, the climate began to dry. The vast equatorial swamps shrank and fragmented. The scale trees, so perfectly adapted to wet, oxygen-rich conditions, found themselves increasingly out of place in a world that was becoming more arid and seasonal. Gradually, other plants better adapted to these new conditions began to dominate. The conifers, early relatives of modern pines and firs, spread across upland areas. The seed ferns diversified, and most crucially, fungi and bacteria finally evolved efficient enzymes for breaking down lignin and cellulose, meaning that dead trees now rotted away rather than accumulating into peat. The coal-forming forests largely disappeared, replaced by ecosystems that recycled their dead plant material rather than preserving it. There would be other periods of coal formation in Earth's history, but never again on the scale of the Carboniferous. That was a unique moment in planetary history. A confluence of factors: high oxygen, high CO2, wet climate, inefficient decomposers, that created conditions perfect for burying massive quantities of carbon and preserving it for hundreds of millions of years. Today, tiny remnants of the scale tree lineage still exist. The club mosses, small plants you might see growing in forests or sold as decorative ground cover, are direct descendants of Lepidodendron and Sigillaria, though they've been reduced to just inches in height. The horsetails, too, persist as small plants growing along streams and in wet areas. These living fossils carry within them the genetic heritage of giants, their DNA encoding instructions for growing structures that once dominated continents but now barely rise above the soil. When you see coal, whether it's a lump in a museum or an entire seam exposed in a road cut, you're looking at a forest, not a modern forest, but an alien landscape of scale trees and giant ferns, a swamp world where the rules were different, and plants grew in forms we can barely imagine. You're seeing millions of years of sunlight, stored and compressed, a snapshot of an atmosphere that no longer exists, preserved in stone. The endless forests of the Carboniferous are gone, but their legacy remains, buried in the earth and burning in our power plants. A reminder that our modern world is built quite literally on the foundations of deep time. The forest floor is alive with movement. All around you, the sounds of the Carboniferous world create a symphony of clicks, buzzes, and rustles as giant arthropods navigate through the ferns and horsetails. You've been walking carefully through the swampy landscape, trying to avoid sinking too deeply into the saturated ground, when you come upon a large pool of murky water, its surface covered with a thick mat of decaying vegetation and floating fern fronds. The water is dark, almost black, and perfectly still. Too still. Something about this stillness makes the hair on the back of your neck stand up, triggers some ancient prey instinct buried deep in your mammalian brain. You're about to turn away when the water explodes. A massive shape erupts from beneath the surface, jaws agape, revealing rows of sharp, conical teeth set in a mouth easily 2 feet long. Water streams off a body that keeps coming and coming. 6 feet, 7 feet, 8 feet of muscular predator, launching itself halfway out of the pool. This is no dinosaur, no reptile, not even close to anything you'd recognize from the modern world. This is Proterogyrinus, one of the most formidable amphibians ever to walk the earth, and you've just witnessed what makes these creatures the undisputed apex predators of the Carboniferous swamps. Welcome to the age of amphibians, a time when our distant ancestors ruled the land with a dominance that would not be matched until the rise of the dinosaurs more than 100 million years later. When most people think of amphibians, they picture frogs sitting on lily pads, salamanders hiding under logs, or perhaps a toad hopping through a garden. Small creatures, mostly harmless, cute even. Delicate animals that need to keep their skin moist and spend half their lives in water. This image couldn't be more misleading when applied to the amphibians of the Carboniferous and early Permian periods. These were not the diminutive descendants we know today. These were monsters, powerful predators that had successfully made the transition from water to land and claimed terrestrial ecosystems as their own private hunting grounds. Proterogyrinus stands as the perfect representative of these ancient giants. Imagine an alligator, but built with the body plan of a salamander, stretched out to lengths of 9 to 10 feet, with a skull alone measuring over a foot long. The body was low-slung and powerful, built close to the ground, supported by 4 stout legs that splayed out to the sides in the classic amphibian sprawl. But don't let that sprawling posture fool you into thinking these creatures were slow or clumsy. Those legs were packed with muscle, capable of explosive bursts of speed that could propel the animal forward in sudden lunges that would catch prey completely off guard. The skull of Proterogyrinus was a masterpiece of predatory engineering, a solid wedge of bone studded with sensory organs and armed with a formidable array of teeth. The snout was relatively long and somewhat narrow, shaped for slicing through water with minimal resistance when the animal lunged at prey. The eyes sat high on the head, positioned perfectly for a creature that spent much of its time submerged, allowing it to see above the water's surface while the rest of its body remained hidden below. This is the anatomy of an ambush predator, an animal that understood the value of patience and the power of surprise. But it's the teeth that really tell the story of what Proterogyrinus was and what it did. The jaws were lined with numerous, sharp, conical teeth, each one curved slightly backward. These weren't teeth designed for chewing or grinding. These were gripping teeth, holding teeth, teeth that impaled prey and prevented any hope of escape. Once Proterogyrinus clamped down on a victim, those backward curving teeth ensured that struggling would only drive them deeper. The bite force, though difficult to calculate precisely for an extinct animal, would have been substantial, easily capable of crushing through the exoskeletons of large arthropods or the bones of smaller vertebrates. The hunting strategy of Proterogervinus would have been brutally simple yet devastatingly effective. Picture this apex predator in its element, a large, shallow pool in a carboniferous swamp. The water murky with tannins and suspended organic matter. The giant amphibian lies submerged in the muck, only its eyes and nostrils breaking the surface, the rest of its body completely invisible against the muddy bottom. It doesn't move, it barely breathes. It simply waits with the infinite patience of a perfect predator. Hours might pass. The sun climbs higher in the sky, filtering down through the canopy of scale trees and tree ferns. Arthropleura passes by on the shore, but it's too large, too well armored, not worth the energy expenditure. A smaller amphibian, perhaps one of the more primitive species, emerges from the undergrowth and approaches the water's edge. It's thirsty, or perhaps hunting for aquatic invertebrates. It leans down toward the water, utterly unaware of the death waiting beneath the surface. Proterogervinus strikes with explosive force. The powerful hind legs drive the body forward, while the front legs push down, helping to launch the predator upward and out of the water. The jaws open impossibly wide, revealing that nightmare array of teeth. The entire attack, from stillness to impact, takes less than a second. The jaws slam shut around the prey with a sound like a trap snapping closed. The victim doesn't even have time to cry out before it's being dragged backward into the pool, pulled down into the dark water where its struggles become increasingly feeble before stopping altogether. This wasn't the only hunting strategy available to Proterogervinus, though. These animals were equally at home on land, and their sprawling gait, while it might look ungainly to our eyes, was perfectly adequate for moving through the cluttered landscape of the Carboniferous forest floor. They could navigate through dense undergrowth, climb over fallen logs, and patrol the shorelines of pools and streams looking for anything edible. The giant insects that dominated this era would have been prime targets. An Arthropleura, for all its armor, would have been vulnerable to a Proterogervinus attack from above, the powerful jaws targeting the joints between segments where the exoskeleton was thinner. The life cycle of Proterogervinus, like that of modern amphibians, would have begun in the water. Adults would have returned to pools and streams to breed, the males perhaps engaging in competitive displays or combat to win access to females. The females would have laid hundreds or even thousands of eggs, depositing them in the water in gelatinous masses, similar to those produced by modern salamanders. These eggs would have hatched into larvae, completely aquatic creatures with external gills and a body plan optimized for swimming. The larvae of Proterogervinus would have been formidable predators in their own right. Even as juveniles, they possessed those characteristic amphibian teeth and predatory instincts. They would have hunted smaller fish, aquatic arthropods, and anything else they could overpower in the underwater environment. As they grew, they wool. Have gradually developed lungs to supplement their gill breathing, and their legs would have grown stronger and more functional. Eventually, after months or perhaps years in the water, they would have undergone metamorphosis, absorbing their gills and emerging onto land as miniature versions of the adults, ready to begin their terrestrial hunting careers. But Proterogervinus was far from alone in its dominance of Carboniferous ecosystems. It was part of a diverse assemblage of large amphibians collectively known as temospondylus, a group that would persist for over 200 million years and produce some of the most impressive amphibians ever to exist. Some of these temospondylus were even larger than Proteroduranus. Archaeopteryx, which lived slightly later in the early Permian, could reach lengths of 6 feet and had a skull built like a battering ram, heavy and broad, capable of delivering bone-crushing bites. Prionocetus, from the Permian of Brazil, may have reached lengths of 30 feet, making it the largest amphibian known to science, a creature that rivaled crocodiles in size and probably in lifestyle. Other Carboniferous amphibians explored different ecological niches. Some species became specialized for life in fast-flowing streams, developing streamlined bodies and powerful tails for swimming against strong currents. Others became more terrestrial, developing stronger legs and spending less time in the water. Still others went in the opposite direction, becoming wreathingly aquatic. Their legs reduced and their bodies elongated into an eel-like form, perfect for swimming. The diversity of these ancient amphibians raises an interesting question. Why did they dominate so completely? Why were there no reptiles or mammals or other terrestrial vertebrates to challenge their supremacy? The answer lies in evolutionary timing and adaptation. Amphibians were the first vertebrates to successfully colonize land. They had a head start of millions of years, time they used to diversify and adapt to every available terrestrial and semi-aquatic niche. They evolved efficient lungs for breathing air. They developed stronger limbs for supporting their weight on land. They perfected the skills necessary for hunting in terrestrial environments. The early reptiles did exist during the Carboniferous, but they were small, marginal creatures occupying ecological niches that the dominant amphibians couldn't or didn't exploit. These early reptiles were innovators, experimenting with a revolutionary new adaptation, the amniotic egg. This egg, with its protective shell and internal membranes that allowed embryos to develop completely on land without returning to water, would eventually allow reptiles to break free from the aquatic dependency that limited amphibians. But in the Carboniferous, this advantage hadn't yet translated into dominance. The amphibians still ruled, and they ruled absolutely. Life for a Proterogyranus would have been governed by the same basic needs that drive all predators: feeding, reproducing, and avoiding injury. The wet, swampy environment of the Carboniferous provided abundant prey but also created challenges. The high humidity and frequent rainfall meant standing water everywhere, which was advantageous for creatures that needed to keep their skin moist. But it also meant competition for prime hunting territories, both from other Proterogyranus individuals and from different species of large amphibians. Territorial disputes between these apex predators must have been spectacular and brutal affairs. Two male Proterogyranus, each claiming the same productive hunting pool, would have engaged in combat that combined the terrestrial aggression of modern crocodiles with the aquatic maneuvering of giant salamanders. They would have lunged at each other with jaws agape, each trying to secure a grip on the other's skull or neck. The sound of their teeth clashing against bone would have echoed through the forest. They would have twisted and rolled, both in the water and on land, each trying to inflict damage while avoiding the same. These battles would have continued until one competitor was driven off, injured, and defeated, leaving the victor in control of valuable hunting territory. The skin of Proterogyrinus, like that of all amphibians, would have been permeable and required moisture to function properly. This meant these animals, despite their success on land, could never stray too far from water. They were tied to wetland environments, dependent on the swamps and pools that characterize the Carboniferous landscape. In areas where the climate was drier or more seasonal, amphibian diversity would have been lower, and other animals would have begun to gain footholds. As powerful as these giant amphibians were, they faced the same existential threat that all amphibians face: drought. If pools dried up during seasonal dry spells, if water became scarce, these massive predators would have been in trouble. Some could probably burrow into mud and enter a state of dormancy, waiting for rains to return. Others might have been able to move overland to find new water sources, but prolonged drought would have been catastrophic for populations of these water-dependent giants. The legacy of these ruling amphibians is written not just in the fossil record, but in the very DNA of every amphibian alive today. The frogs, toads, salamanders, and caecilians of the modern world are all descendants of this ancient lineage that once dominated the planet. They carry within them genetic instructions that were honed in an era when their ancestors were the most fearsome predators on land. The hunting instincts of a modern bullfrog waiting to ambush prey are the same instincts that drove Proterogyrinus. The powerful legs that allow a salamander to lunge forward are built on the same basic template that evolution crafted hundreds of millions of years ago. The age of amphibian dominance would eventually end. Of sea, ours. As the climate continued to change, as the wet Carboniferous gave way to the drier Permian, as reptiles evolved and diversified and exploited their freedom from water dependency, the giant amphibians began to decline. They didn't disappear entirely. Some lineages persisted well into the Mesozoic era, sharing the world with dinosaurs. But they would never again achieve the dominance they enjoyed during those ancient times when a Proterogyrinus could lurk in a swamp pool, the undisputed master of its domain, waiting patiently for the next meal to wander within striking distance of those terrible jaws. While Proterogyrinus and its amphibian kin ruled the swamps with tooth and claw, stalking through the shallow waters as undisputed apex predators, something revolutionary was happening in the margins of their world. In the drier uplands, in the leaf litter beneath fallen scale trees, in rocky outcrops far from the life-giving pools that amphibians required, a new kind of creature was quietly writing the next chapter of Earth's story. These animals were small, unimpressive to look at, easily overlooked amid the giants that dominated the Carboniferous landscape. They scurried through the undergrowth on legs that seemed too long for their bodies, their movements quick and nervous, always alert for the shadows of Meganeura overhead, or the approach of a hungry amphibian. But these humble creatures carried within them an innovation so profound, so transformative, that it would eventually reshape life on Earth and led, millions of years down the line, to the age of dinosaurs. These were the first true reptiles, and they had solved one of evolution's most challenging problems: how to reproduce without returning to water. To understand why this matters, we need to step back and consider the fundamental constraint that limited the amphibians despite all their success. An amphibian, no matter how large or fearsome, no matter how well adapted to terrestrial life it might be, is ultimately a prisoner of its reproduction. When breeding season arrives, it must return to water. The eggs it produces are soft, unprotected, covered only in a gelatinous coating that prevents them from drying out but offers no real defense against the elements or predators. These eggs must be laid in water or in extremely moist environments. They cannot survive desiccation. This means that amphibians, no matter how far they might roam during their adult lives, are forever tethered to aquatic environments by the needs of their offspring. The early reptiles shattered this constraint with one of the most important evolutionary innovations in the history of vertebrate life: the amniotic egg. Now, an egg might not seem like the most exciting topic compared to giant predators and insects the size of hawks, but bear with me, because this is arguably the most revolutionary development we'll discuss. The amniotic egg is a self-contained life support system, a portable pond that allows an embryo to develop completely on land, independent of any external water source. Let me paint you a picture of what made this egg so special. Imagine holding one in your hand, perhaps the egg of Helenomus, one of the earliest known reptiles, a creature no bigger than a modern lizard. The first thing you'd notice is the shell, a leathery, flexible covering quite different from the hard, brittle shells of bird eggs we're familiar with today. This shell is semi-permeable, allowing oxygen to pass through to the developing embryo inside while preventing water loss. It's a barrier against the outside world, protecting the precious contents from predators, parasites, and most importantly, from drying out. Crack open that shell carefully, and you'd discover an intricate arrangement of membranes, each one serving a specific function. The outermost membrane, just beneath the shell, is the chorion, which facilitates gas exchange, acting like a lung for the developing embryo. Beneath that is the amnion, the structure that gives the amniotic egg its name. The amnion creates a fluid-filled sac around the embryo itself, a private ocean in which the developing reptile can float, cushioned and protected. This amniotic fluid is the portable pond, allowing the embryo to develop in an aquatic environment, even though the egg itself might be buried in dry soil or hidden under a rock, far from any water source. There's more. Another membrane called the allantois serves as both a respiratory surface and disposal system, collecting the embryo's waste products and storing them safely away from the developing animal. And surrounding everything is the yolk sac, a massive reservoir of nutrients that will sustain the embryo throughout its entire development. Unlike an amphibian tadpole, which must hatch quickly and begin feeding while still in a relatively undeveloped state, a reptile embryo can remain in its egg for weeks or even months, growing and developing until it emerges as a fully formed miniature version of the adult, ready to fend for itself from day one. This might seem like a subtle difference, just a matter of having a better egg, but the implications were staggering. With the amniotic egg, reptiles were no longer tied to water for reproduction. A female reptile could lay her eggs anywhere that offered suitable temperature and protection, in sandy soil, in burrows, under rocks, in rotting logs, even in the dry uplands far from any pool or stream. This freedom meant that reptiles could colonize habitats that were completely off limits to amphibians. They could venture into drier regions, exploit food sources in areas where amphibians couldn't survive, and escape competition with the dominant amphibian predators by simply going where those predators couldn't follow. The earliest known reptile, or at least the earliest we've discovered in the fossil record, is Hylonomus lielli, whose remains were found in the fossilized stumps of Carboniferous scale trees in Nova Scotia. These ancient trees, when they died and fell, left hollow stumps that acted as natural pit traps. Small animals, likely seeking shelter or hunting for insects, would fall into these stumps and become trapped, unable to climb the smooth interior walls. Over time, their remains were buried and fossilized, creating a snapshot of the small vertebrate community of the late Carboniferous. Hylonomus was tiny by the standards of its time, measuring only about 8 inches long from nose to tail. It had a lizard-like appearance with a slender body, long tail, and relatively long legs that held its body up off the ground, more than the sprawling stance of amphibians. The skull was small and lightly built, with sharp teeth suggesting a diet of insects and other small invertebrates. Everything about Hylonomus spoke of a creature living life in the fast lane, quick and agile, darting through the leaf litter and climbing through the undergrowth in search of prey. But despite its small size and unassuming appearance, Hylonomus represented a radical new body plan, one that would prove to be spectacularly successful. The key differences from amphibians weren't necessarily visible in the skeleton alone, though there were subtle changes in the skull bones, the structure of the vertebrae, and the attachment points for muscles. The real revolution was in the soft tissues, in the skin that was less permeable and better at retaining moisture, in the more efficient kidneys that conserved water, and most importantly, in the ability to produce those revolutionary amniotic eggs. The world that these early reptiles inhabited was still very much the world of the amphibians. Proterogyrinus and its kin were the dominant predators, the animals that controlled the prime hunting territories and consumed the majority of available prey. The giant arthropods still crawled and flew through the forests. The scale trees still towered overhead. But in the shadows, in the margins, the reptiles were establishing themselves, learning, adapting, slowly building toward their future dominance. Other early reptiles began appearing in the fossil record alongside Hylonomus. Paleothyrus was another small insectivore, similar in many ways to Hylonomus, but showing slight variations in skull structure and proportions. Petrolacosaurus had even longer legs and a more slender build, suggesting it might have been an especially fast runner, perhaps already evolving the speed and agility that would characterize many later reptile lineages. These animals were pioneers, the vanguard of a revolution that would unfold over millions of years. The advantages of the amniotic egg became more pronounced as the climate began to change. The Carboniferous period, with its wet, swampy conditions and stable tropical climate, was ideal for amphibians. But nothing in Earth's history remains static forever. Continental drift was slowly reconfiguring the land masses. The vast coal swamps were beginning to dry out in some regions. Climate patterns were shifting, becoming more seasonal, with wet and dry periods rather than constant humidity. These changes, subtle at first, spelled trouble for creatures dependent on standing water for reproduction. The reptiles, meanwhile, thrived in these changing conditions. A drought that would devastate amphibian populations barely affected reptiles, who could lay their protected eggs in underground burrows where moisture was retained. Seasonal dry spells that killed amphibian eggs wholesale left reptile eggs untouched in their leathery shells. Gradually, incrementally, the balance began to shift, but we must be careful not to paint this as a simple story of superior reptiles replacing inferior amphibians. Evolution doesn't work that way. The early reptiles weren't better than amphibians in any absolute sense. They were simply different, with different strengths and weaknesses, different adaptations and constraints. In the wet lowland swamps that would persist for millions of years, amphibians continued to dominate. They were larger, stronger, better adapted to aquatic hunting. A Hylonomus wouldn't stand a chance against a Proterogyrinus in direct competition. The reptiles succeeded by avoiding that competition, by exploiting niches and habitats where their particular suite of adaptations gave them an advantage. Think of it this way. The amphibians had claimed the aquatic and semi-aquatic environments completely. They were the masters of the swamps and ools. But the reptiles opened up a new frontier. They colonized the dry uplands, the rocky hillsides, the seasonal forests where pools dried up for months at a time. They went where amphibians couldn't go, ate foods that amphibians couldn't access, and slowly, over millions of years, diversified into an astonishing array of forms. From these humble beginnings, from creatures no larger than modern lizards scurrying through the Carboniferous undergrowth, the reptiles would eventually produce the most spectacular diversity of land animals Earth has ever seen. The lineage would split and split again, branching into countless evolutionary experiments. One branch would lead to the turtles, developing their distinctive protective shells. Another would produce the lizards and snakes, masters of the dry land with their scaly skin and highly efficient kidneys. Yet another branch would give rise to the archosaurs, and from them would come the crocodilians, the pterosaurs, and, most famously, the dinosaurs. But all of that was still far in the future. At the end of the Carboniferous period, around 300 million years ago, the reptiles were still marginal players, small insectivores living in the shadow of giant amphibians. If you could have surveyed the vertebrate fauna of that time and been asked to predict which group would dominate the future, you almost certainly would have bet on the amphibians. They were bigger, more numerous, more diverse, more successful by every measure. Hats seemed to matter, yet the reptiles had planted a seed, an innovation that would germinate slowly over millions of years. The amniotic egg was a key that unlocked doors the amphibians didn't even know existed. It was a passport to new territories, new lifestyles, new evolutionary possibilities. And while it would take another 100 million years for that potential to be fully realized, while countless generations of small reptiles would live and die before their descendants would grow to dominate the earth, the foundation had been laid. The first reptiles emerged not with a roar, but with a whisper, not by conquering, but by finding their own path. They were the quiet revolution, the incremental change that would eventually transform everything. In the history of life on Earth, few innovations have proven as consequential as that first amniotic egg, laid somewhere in a Carboniferous forest by a small, unassuming creature that had no idea it was changing the world. When we look at the diversity of reptiles today, from tiny geckos to massive saltwater crocodiles, from desert-dwelling horned lizards to sea turtles crossing oceans, we're seeing the legacy of that Carboniferous innovation still unfolding. And when we watch birds, the living dinosaurs, soaring through the sky or perching in trees, we're witnessing the continuation of a story that began with creatures like Hylonomus, small pioneers who happened upon an evolutionary solution that freed them from water and opened the entire terrestrial world to their descendants. The age of amphibians was reaching its peak, but the age of reptiles was beginning, and with it, the long road that would eventually lead to the thunder lizards, the dinosaurs that would one day rule a world their tiny ancestors could never have imagined. Time marches forward, and the earth transforms beneath our feet. Millions of years have passed since we watched Hylonomus scurry through the Carboniferous undergrowth, since Proterogeranus lurked in those ancient swamps, since Meganeura ruled skies thick with oxygen. The planet is changing, shifting, becoming something different. The endless coal forests are retreating, their reign coming to an end as the climate grows drier and more seasonal. The oxygen levels that once soared to 35% are declining, dropping back toward more moderate levels. The sprawling swamps are giving way to new landscapes, deserts, dry scrublands, seasonal forests that experience both rain and drought. And in these new environments, a new cast of characters is taking center stage. Welcome to the Permian period, the final chapter of the Paleozoic era, spanning from 299 to 252 million years ago. This is when Earth's story takes a turn into even stranger territory, when evolution experiments with body plans so bizarre, so alien, that they make the Carboniferous giants look almost conventional by comparison. Stand with me now on a Permian land. Scape and feel how different everything is. The air is drier, less humid, easier to breathe, but somehow less vital than the oxygen-charged atmosphere of the Carboniferous. The temperature varies more dramatically between day and night, between seasons. The ground beneath your feet is harder, less waterlogged, covered in places with a reddish soil that hints at the oxidation of iron minerals in a more arid climate. The plant life has changed too. The scale trees and giant horsetails are largely gone, replaced by seed ferns, early conifers that look like primitive pine trees, and cycad-like plants with thick, palm-like fronds. But it's the animals that truly signal how much the world has changed. The giant amphibians are still around, still formidable, but they're no longer the undisputed rulers they once were. Their dominance is fading as the wet environments they depend on become scarcer. And stepping into the spotlight, claiming the role of apex predators and dominant herbivores, is a group of creatures that most people have never heard of. Animals that are neither reptile nor mammal, but something in between, something entirely their own. These are the synapsids, often called mammal-like reptiles, though that name is somewhat misleading and despised by many paleontologists. They're not really reptiles at all, but rather represent a separate lineage that split from the reptiles, very early in amniote evolution. They're your ancestors more directly than any dinosaur or lizard. could ever claim to be. The synapsids are the line that will eventually, millions of years down the road, give rise to mammals, to everything from mice to elephants, from bats to whales, and yes, to humans. But in the Permian, they're still experimenting, still trying out different evolutionary strategies, creating forms that defy easy categorization. The defining characteristic of synapsids, the feature that gives them their name, is a single opening in the skull behind each eye socket, a temporal fenestra that distinguishes them from the anapsids, which have no such openings, and the diapsids, which have two. This might seem like an arcane anatomical detail, but these skull openings are crucial. They provide space for more powerful jaw muscles to attach, allowing for stronger, more efficient bites. This adaptation would prove extraordinarily successful, helping synapsids become the dominant terrestrial vertebrates of the Permian period. The early Permian synapsids were relatively small creatures, not much larger than the early reptiles we discussed. Creatures like Archaeothrus looked superficially similar to lizards, with sprawling legs and long tails, hunting insects and small vertebrates in the undergrowth. But as the period progressed, synapsids began to diversify explosively, splitting into two major groups that would dominate different ecological niches. The first group, the Pelycosaurs, included some of the most iconic prehistoric animals, even though most people don't realize they're not dinosaurs. These were the early synapsid experimenters, trying out various body plans and lifestyles. Some remained small insectivores, others grew large and became top predators. Still others evolved into herbivores, the first vertebrates to truly specialize in eating plants as their primary food source. This last innovation was revolutionary. Until the Permian, almost all large vertebrates were predators. But plants represent an enormous, largely untapped food source, and the synapsids that learned to exploit it had access to effectively unlimited calories. Picture yourself now in a middle Permian landscape, perhaps in what is today Texas or Oklahoma, regions that were near the equator during this ancient time. The sun beats down from a cloudless sky, and the heat is intense. In the distance you see a herd of strange creatures moving slowly across the landscape, grazing on the tough, fibrous vegetation. These are Edaphosaurus, herbivorous synapsids built like living barrels, their bodies massive and rotund, their legs splayed out to the sides in that characteristic primitive sprawl. But what immediately catches your eye is the extraordinary sail rising from each animal's back. These sails are formed by elongated neural spines, extensions of the vertebrae that project upward, sometimes reaching heights of several feet. The bones are covered with skin, creating a broad, fan-like structure that runs down the length of the animal's back from the shoulder to the hips. But unlike simple, smooth sails, those of Edaphosaurus are studded with bony knobs and crossbars, creating a textured surface that looks almost decorative. Scientists still debate the function of these sails. Were they for temperature regulation, acting like solar panels to warm the animal in the cool morning or like radiators to shed excess heat in the afternoon? Were they for display, to make the animal look larger and more impressive to rivals or to attract mates? Or did they serve multiple functions? The mystery remains unsolved, but there's no denying their visual impact. Watch an Edaphosaurus for a while, and you'll notice something else unusual. The skull is small relative to the massive body, and the jaws are equipped with specialized teeth unlike those of any predator. The front teeth are small and peg-like, useful for cropping vegetation, while the back of the mouth and even the roof are lined with patches of small, grinding teeth. This is a sophisticated plant processing system, allowing the animal to break down tough plant material and extract nutrients. The digestive system must have been equally specialized, probably housing colonies of bacteria to help ferment and break down cellulose, the tough structural material that makes up plant cell walls. But predators are never far away in any ecosystem. Movement in the scrubland catches your attention, and you turn to see another sailed synapsid emerging from behind a cluster of ferns. This one is built very differently from the herbivorous Edaphosaurus. This is Dimetrodon, one of the most successful predators of the early to middle Permian, and it's approaching the herd with deadly intent. Dimetrodon is built for killing. The body is lean and muscular, about 11 feet long from nose to tail tip, with powerful legs that can deliver surprising bursts of speed despite their sprawling configuration. The skull is large, almost disproportionately so, and filled with differentiated teeth that tell a story of specialized predation. The front teeth are like daggers, long and sharp, perfect for stabbing and holding prey. Behind them are thicker, more robust teeth designed for slicing through flesh and crushing bone. This is one of the first examples of heterodonty, different types of teeth for different functions, a feature that would become standard in mammals but was revolutionary in the Permian. Like Edaphosaurus, Dimetrodon sports a dramatic sail on its back, but this one is smooth, formed by tall neural spines covered in skin but without the bony decorations. The sail catches the morning sunlight, and you can almost imagine it functioning as a solar panel, warming the predator's blood and giving it an energy advantage over prey that might still be sluggish from the cool night. Or perhaps it's a signaling device, a way for Dimetrodon to communicate with rivals and potential mates from a distance, the sail visible over the scrub vegetation. The hunt unfolds with patient precision. Dimetrodon doesn't charge recklessly into the herd. Instead, it studies the Edaphosaurus carefully, looking for weakness, for an individual that's young or sick, or simply separated from the group. The herbivores are aware of the predator now, their heads turning to track its movement, their bodies tensing. But they don't flee immediately. They're large, heavy animals, and running is expensive in terms of energy. They wait, watching, hoping the predator will move on. But Dimetrodon has identified its target, a younger Edaphosaurus on the edge of the herd, not quite fully grown, potentially inexperienced. The predator's muscles coil, and then it strikes, legs churning as it accelerates toward the victim. The young Edaphosaurus tries to run, but its body isn't built for speed. The sprawling leg posture means that much of the animal's energy goes into side-to-side motion rather than forward momentum. Dimetrodon closes the distance with terrifying speed. The attack, when it comes, is brutal and efficient. Dimetrodon's jaws open wide, revealing those specialized teeth, and then clamp shut on the Edaphosaurus's flank. The long front teeth puncture deep into the body cavity, while the crushing teeth in back crack through ribs. The victim bellows in pain and tries to pull away, but Dimetrodon has already secured its grip. The predator's powerful neck muscles engage, thrashing back and forth, tearing flesh, inflicting massive trauma. The struggle is brief. Within minutes, the young Dilophosaurus collapses, and Dimetrodon begins to feed while the rest of the herd moves away, already forgetting their fallen member. This scene, predator and prey, hunter and hunted, played out countless times across the Permian landscapes. But Dimetrodon and Dilophosaurus were just two players in an increasingly diverse and complex ecosystem. Other synapsids were experimenting with even more specialized forms. The therapsids emerged later in the Permian, representing a more advanced group of synapsids that were evolving features that would eventually characterize mammals. These creatures had legs that were beginning to shift from the sprawling reptilian posture toward a more upright stance, moving underneath the body rather than splaying out to the sides. This change might seem subtle, but it had profound implications for locomotion. An upright stance is far more energy efficient, allowing for sustained running and higher stamina. It also raises the body off the ground, improving breathing efficiency during locomotion. The therapsid skull was also evolving, becoming more sophisticated. The jaw joints were repositioning, the muscles were reorganizing, and the teeth were becoming even more differentiated. Some therapsids were developing a secondary palate, a shelf of bones separating the nasal passages from the mouth, allowing them to breathe while eating. This is a mammalian feature, something we take for granted, but in the Permian, it was cutting-edge innovation. Some therapsids grew to enormous sizes. Moschops, a herbivore from South Africa, was built like a living tank, with a massive barrel-shaped body, thick legs, and a skull reinforced with bone so thick it could potentially be used for headbutting rivals. Titanophanius from Russia was a predatory therapsid with a skull over 2 feet long, armed with enormous canine-like teeth that could deliver devastating bites. But perhaps the most impressive Permian synapsids were yet to come. As the period progressed, a group called the Gorgonopsids evolved into the apex predators of their time. These creatures, which we'll explore in more detail shortly, developed saber teeth and hunting behaviors that wouldn't be seen again until the evolution of saber-toothed cats millions of years later. The Permian world was a laboratory of evolution, a testing ground where nature tried out body plans and strategies that would influence the entire future of vertebrate life. The synapsids dominated this era so completely that it's sometimes called the Age of Synapsids, though that name never quite caught on the way Age of Dinosaurs or Age of Mammals did. But for nearly 50 million years, these strange-sailed, increasingly mammal-like creatures owned the earth. They diversified into every available niche. There were tiny insectivores no bigger than shrews, medium-sized omnivores, massive herbivores, and fearsome predators. They spread across every continent, adapting to deserts, forests, scrublands, and river valleys. They evolved specialized diets, complex behaviors, and increasingly sophisticated physiology. They were becoming warm-blooded, developing better temperature regulation. They were growing hair, at least in some lineages, providing insulation and sensory functions. They were, step by step, generation by generation, becoming more mammalian, but they couldn't have suspected that their reign was approaching a catastrophic end. The Permian period, for all its evolutionary innovation and biological diversity, was racing toward the greatest mass extinction event in Earth's history. A cataclysm so severe that it would nearly erase complex life from the planet entirely. The synapsids, for all their success, for all their evolutionary sophistication, were about to face their ultimate test, and most would fail. The stage was being set for the great dying, and nothing in the Permian world could prepare these strange giants for what was coming. Let's pause our journey through the Permian and focus on one creature in particular, because this animal deserves our full attention. You've almost certainly seen it before, perhaps as a plastic toy mixed in with a child's dinosaur collection, or in illustrations of prehistoric life, or featured in documentaries about ancient worlds. Its silhouette is unmistakable, that magnificent sail rising from its back, the powerful predatory body, the fearsome jaws. Most people assume they're looking at a dinosaur, one of those terrible lizards that dominated the Mesozoic. But they're wrong, completely and utterly wrong, and that mistake actually makes Dimetrodon far more interesting than if it were just another dinosaur. Dimetrodon lived and died and went extinct nearly 40 million years before the first dinosaur ever drew breath. When T-Rex was stalking its prey through Cretaceous forests, when Brachiosaurus was browsing on treetops, when Velociraptors were hunting in packs, Dimetrodon had already been extinct for longer than the entire age of dinosaurs would last. This creature is ancient beyond ancient, a predator from a world so different from the age of dinosaurs that they might as well have existed on different planets. And more than that, Dimetrodon isn't even a reptile. It's a synapsid, a member of the lineage that would eventually lead to mammals, making it more closely related to you than it ever was to any dinosaur. Let's go back, way back, to the early Permian period, approximately 295 million years ago. The location is what paleontologists call the red beds of Texas and Oklahoma, though of course those place names wouldn't exist for hundreds of millions of years. The landscape is semi-arid, a patchwork of scrubland and seasonal forests interrupted by river systems and temporary lakes that swell during the rainy season and shrink to mud during droughts. The temperature swings wildly between the scorching heat of day and the surprising chill of night. Talking through this environment, the undisputed apex predator of its ecosystem is Dimetrodon grandis, the largest and most fearsome species of its genus. An adult Dimetrodon grandis is an impressive sight. From nose to tail tip, it measures up to 15 feet in length, though much of that is tail. The body itself is powerfully built, perhaps weighing between 500 and 600 pounds, with a barrel-like torso supported by 4 sturdy legs. Those legs splay out to the sides in the characteristic sprawling posture of primitive synapsids, meaning that when the animal walks, its body sways from side to side with each step, the belly close to the ground. This isn't the most efficient way to move, not compared to the upright stance that later animals would evolve, but Dimetrodon makes it work through sheer muscular power. But it's the head that immediately identifies this as a predator built for killing. The skull is massive, nearly 16 inches long in the largest individuals, and accounts for a significant portion of the animal's body length. It's shaped almost like a wedge, narrow at the snout and broadening toward the back, creating a profile that seems to scream aggression. The jaws are deep and powerful, packed with muscles that can generate tremendous bite force. And filling those jaws is an arsenal of teeth that represents one of evolution's great innovations in predatory design. Look closely at those teeth, and you'll see something that didn't exist in early predators. They're not all the same. In the front of the mouth are large, dagger-like teeth, canine-form teeth that are longer and more robust than the others. These are stabbing weapons, designed to puncture deep into prey, to grip and hold while the victim struggles. Behind these are smaller, sharper teeth with serrated edges, cutting tools that can slice through flesh and muscle with terrifying efficiency. Further back are thicker, more robust teeth capable of crushing bone. This differentiation, this heterodonty, is one of the first examples in vertebrate evolution of specialized teeth working together as an integrated toolkit. Later mammals would refine this system even further, but Dimetrodon was already exploring the concept millions of years before mammals existed. The eyes are positioned on the sides of the skull, providing good peripheral vision useful for detecting movement across a wide field of view. The nostrils sit at the end of the snout, and evidence suggests that Dimetrodon had a reasonably good sense of smell, useful for tracking prey or detecting carrion. This was a hunter that used multiple senses to locate food, a sophisticated predator capable of both active hunting and opportunistic scavenging. But we haven't yet addressed the feature that makes Dimetrodon instantly recognizable, the anatomical quirk that has made it an icon of prehistoric life. That magnificent sail, rising from the animal's back, supported by tremendously elongated neural spines. Extending from the vertebrae, this sail reaches heights of over 3 feet at its tallest point. The spines themselves are extensions of the backbone, growing upward from each vertebra along the animal's spine from the shoulders all the way back to the hips. These spines are covered with skin that was almost certainly rich in blood vessels, creating a broad, thin surface area that would have been highly vascularized. For over a century, scientists have debated the function of this extraordinary structure. The leading hypothesis, and the one supported by the most evidence, is that the sail functioned primarily as a thermoregulatory device, a biological solar panel and radiator combined into one elegant structure. Let me walk you through why this makes sense and why it matters. Dimetrodon lived in an environment with dramatic temperature fluctuations. During the Permian day, especially in the semi-arid environments where Dimetrodon fossils are most commonly found, temperatures could soar to uncomfortable levels, but at night, with no cloud cover to trap heat and relatively little vegetation to moderate temperature, the environment could cool dramatically. This created a problem for a large-bodied predator. Like modern reptiles, Dimetrodon was probably ectothermic, or at least not fully endothermic, meaning it couldn't generate body heat efficiently through metabolism the way mammals do. It relied heavily on external heat sources to warm its body to operating temperature. Here's where the sail becomes crucial. In the early morning, as the sun rises and begins warming the landscape, a Dimetrodon positions itself broadside to the sun's rays. The sail, with its large surface area and rich blood supply, acts like a solar collector. Blood flowing through the vessels in the sail absorbs heat directly from the sun, and this warmed blood circulates back into the body core, raising the animal's overall temperature. Mathematical models suggest that a Dimetrodon with a sail could warm up to operating temperature as much as 30 to 40% faster than a similarly sized animal without a sail. Why does this matter? Because in a predator's world, the early bird gets the worm, or in this case, the warm predator catches the prey. If Dimetrodon could achieve full activity levels, while its prey was still sluggish from the cool night, it gained an enormous hunting advantage. It could ambush animals that were too cold to flee effectively. It could patrol territory and search for food while competitors were still warming up. In evolutionary terms, this gave Dimetrodon a significant edge, but the sail worked both ways. During the heat of the day, if the animal's body temperature started to climb too high, Dimetrodon could position itself in the shade or orient the sail to minimize sun exposure. The same blood vessels that absorbed heat in the morning could now radiate excess heat away, cooling the blood before it circulated back into the body. The sail could even see hatch breezes, increasing convective cooling. In this way, Dimetrodon could actively manage its body temperature, maintaining it within an optimal range for activity and avoiding both the lethargy of cold and the danger of overheating. This temperature regulation would have been revolutionary. Most creatures of the early Permian were entirely at the mercy of environmental temperature. When it was cold, they were sluggish. When it was hot, they had to seek shelter or risk death from hyperthermia. But Dimetrodon, with its sail, had a degree of control. It could exploit times of day when others couldn't. It could remain active across a broader range of conditions. This was one of the first steps toward endothermy, toward the internal temperature regulation that would eventually become standard in mammals and birds. But here, it was being achieved through innovative anatomy rather than metabolic heat production. Of course, not all scientists agree with the thermoregulation hypothesis. Some have suggested the sail was primarily a display structure used for communication and social signaling. In this interpretation, the sail would have been brightly colored or patterned, making each individual distinctive. Males might have had larger or more ornate sails, used to intimidate rivals and attract mates. The size and condition of the sail could have signaled an individual's health and genetic quality, playing a role in sexual selection. There's also no reason both functions couldn't be true simultaneously. Evolution often co-opts existing structures for multiple purposes. The sail could have originated as a thermoregulatory adaptation, but subsequently been elaborated through sexual selection, becoming larger and potentially more colorful than pure temperature regulation would require. Many modern animals have features that serve both practical and social functions, and there's no reason Dimetrodon would be different. What we know for certain is that the sail worked. Dimetrodon was spectacularly successful, dominating early to middle Permian ecosystems across a wide geographic range for millions of years. Fossils have been found across Texas, Oklahoma, New Mexico, and even into more northern regions. Multiple species have been identified, ranging in size from relatively small forms about 6 feet long to the massive Dimetrodon grandis we've been discussing. This diversity suggests that Dimetrodon had adapted to various ecological niches and prey types. The hunting behavior of Dimetrodon can be inferred from its anatomy and from the fossil record of its prey. The powerful jaws and specialized teeth suggest it could tackle a wide variety of animals. Smaller Dimetrodon species probably hunted large insects, early reptiles, and small synapsids. The larger species would have been capable of taking down substantial prey, including the herbivorous synapsids like Edaphosaurus that shared their environment, as well as large amphibians that still persisted in the wet areas. The attack strategy was probably a combination of stalking and ambush. Dimetrodon wasn't built for sustained high-speed chases. That sprawling leg posture and heavy body weren't conducive to marathon pursuits. Instead, the predator likely relied on stealth and explosive acceleration over short distances. It would have used available cover, rocks, vegetation, terrain features to approach prey undetected. Then, when close enough, it would have launched itself forward in a sudden rush, jaws agape, aiming to sink those specialized teeth into the victim before it could escape. Once the teeth found purchase, the powerful neck muscles would thrash the head side to side, tearing flesh and inflicting massive trauma, a killing technique that would later be employed by crocodilians and various dinosaurs. Bite marks on fossil bones of potential prey species show evidence of attacks by large predators with differentiated teeth, consistent with Dimetrodon. Some of these bones show signs of healing, indicating that not every attack was successful, that sometimes prey escaped despite being bitten. This gives us a window into the brutal reality of Permian ecosystems, where every day was a struggle for survival and hunting success was never guaranteed. Dimetrodon likely had few predators to fear once it reached adult size. As the apex predator of its environment, it would have been dangerous for anything to attack. However, juveniles would have been vulnerable to other predators, including adults of their own species. Evidence suggests that Dimetrodon may have been cannibalistic, with larger individuals occasionally feeding on smaller ones. This is common in many modern predators and helps regulate population density. The end came for Dimetrodon not through competition or predation but through environmental change. As the Permian period progressed, climates continued to evolve, ecosystems shifted, and new, more advanced synapsids evolved. The therapsids, with their more upright leg posture and more sophisticated physiology, gradually outcompeted the pelycosaurs like Dimetrodon. By the Middle Permian, around 270 million years ago, Dimetrodon had disappeared from the fossil record, replaced by animals that were, in many ways, its evolutionary descendants but improved upon its basic design. Yet Dimetrodon's legacy persists. The innovations it pioneered, differentiated teeth, active temperature regulation, powerful predatory adaptations, all of these would be refined and passed down through subsequent generations of synapsids. The line that led from Dimetrodon through the therapsids through the cynodonts eventually produced the first true mammals. And those mammals, our ancestors, inherited traits that Dimetrodon had been developing hundreds of millions of years earlier. When you bite into food with different types of teeth working together, when your body maintains a St. 80 temperature. Despite external conditions, You're using innovations that Dimetrodon helped pioneer in an ancient world of sails and sprawling legs, and semi-arid river valleys under an alien sky. As the Permian period matured and entered its final chapters, the world witnessed the rise of predators so advanced, so terrifyingly efficient, that they represented the absolute pinnacle of pre-dinosaur evolution. Dimetrodon and its kin had long since vanished, replaced by more sophisticated hunters. And among these new apex predators, one group stood above all others. A lineage of saber-toothed killers so formidable that they would dominate late Permian ecosystems with an iron grip, the Gorgonopsids, named after the Gorgons of Greek mythology, those monstrous sisters whose gaze could turn men to stone. Picture the late Permian landscape, roughly 260 million years ago. The environment is harsh, the climate increasingly unstable, and moving through this world with lethal grace is Dinosaur, the largest and most powerful of all Gorgonopsids. This creature is massive, reaching lengths of up to 12 feet and weighing perhaps 600 pounds of pure predatory muscle. But size alone doesn't capture what made Gorgonopsids so extraordinary. It's the details, the anatomical innovations, that reveal just how advanced these animals had become. The first thing you notice is the posture. Unlike Dimetrodon with its sprawling reptilian stance, Dinosaur carries its body differently. The legs are positioned more underneath the body, approaching a semi-upright stance that's far more efficient for locomotion. This means the animal can move with greater speed and endurance, can sustain pursuit over longer distances, can turn more quickly when prey attempts to evade. The Gorgonopsids were built for active, aggressive hunting in ways that earlier synapsids simply weren't. But it's the skull that truly takes your breath away. Long and narrow, almost wolf-like in its proportions, the head is a masterpiece of predatory engineering. The temporal fenestrae, those skull openings characteristic of synapsids, have enlarged dramatically, providing space for massive jaw muscles that could generate devastating bite forces. The jaw joint itself has been repositioned, allowing for a wider gape than any predator before it. And then there are the teeth, those magnificent, terrible teeth. The canines of a Gorgonopsid are sabers. There's no other word for them. In Dinosaur, these upper canines can reach lengths of 5 inches or more, curving backward like scimitars, flattened from side to side into blade-like structures with serrated edges. These aren't simple puncturing teeth. These are weapons designed for inflicting catastrophic wounds, for slicing through flesh and severing blood vessels, for killing large, dangerous prey with surgical precision. The lower jaw is deep and robust, providing a stable platform for the enormous upper canines to work against. When the mouth closes, those saber teeth slide past the lower jaw in a shearing action that would have been absolutely devastating. But here's what makes Gorgonopsids truly remarkable. From an evolutionary perspective, they had evolved features that wouldn't become common again until the age of mammals, tens of millions of years later. The skull shows evidence of a secondary palate, that shelf of bones separating the nasal passages from the mouth, allowing the animal to breathe while eating. This might seem trivial, but it's a sophisticated adaptation that indicates improved respiratory efficiency. The teeth showed different types for different functions, with small incisors at the front, those massive canines, and smaller post-canine teeth behind, suggesting complex food processing abilities. Even more tantalizing are hints that Gorgonopsids might have been warm-blooded, or at least approaching endothermy. The bone structure shows characteristics associated with high metabolic rates. The posture and build suggest an active lifestyle that would require sustained energy output. Some scientists speculate they may have even had fur or hair-like covering, providing insulation. Those soft tissues rarely preserve, and we may never know for certain. Watch an Australasia hunt, and you witness predation elevated to an art form. The target is a large Dicinodont, a herbivorous synapsid the size of a cow, peacefully grazing on tough vegetation. The Gorgonopsid approaches upwind, using every scrap of cover, moving with a fluid grace that seems impossible for something so large. Those semi-upright legs allow for a stalking gait that's both quiet and efficient, the body held steady rather than swaying side to side. When the distance closes to perhaps 20 yards, Australasia explodes into action. The acceleration is shocking, powerful muscles driving those improved legs in a sprint that quickly closes the gap. The Dicinodont looks up too late, realizes the danger, and tries to run, but it's already over. The Gorgonopsid strikes from the side, those massive jaws opening impossibly wide, and then slamming shut with those saber teeth driving deep into the victim's throat. The upper canines pierce through hide and muscle, finding the jugular vein and carotid artery. The lower jaw anchors the bite, and then the Gorgonopsid's powerful neck muscles engage, twisting and tearing. The Dicinodont struggles, but it's futile. Those saber teeth have inflicted mortal wounds, severing major blood vessels, and blood pressure drops rapidly. Within seconds, the prey weakens. Within a minute, it's over. Is precision killing, the application of specialized anatomy to dispatch prey quickly and efficiently, minimizing danger to the predator. A Gorgonopsid didn't need to engage in prolonged struggles or risk injury from desperate prey. The saber teeth did their terrible work, and the hunt concluded with clinical efficiency. The Gorgonopsids diversified into numerous species across the late Permian world. Some were relatively small, perhaps only 3 feet long, specialized for hunting smaller prey. Others, like Australasia, grew to enormous sizes. They spread across what is now Russia, South Africa, and other regions, dominating their respective ecosystems as apex predators. For millions of years, nothing could challenge them. They were the culmination of synapsid evolution, the most advanced predators Earth had yet produced. And yet, despite their sophistication, despite their evolutionary success, despite possessing features that seemed to point toward a mammalian future, the Gorgonopsids were doomed. The late Permian was approaching a catastrophe of unimaginable proportions. The greatest mass extinction in Earth's history was bearing down on them, and these magnificent predators, these saber-toothed killers that had perfected the art of the hunt, would be among its victims. The Gorgonopsids would disappear completely, leaving behind only fossils and the tantalizing suggestion of what might have been. Their lineage cut short, just as it seemed poised to inherit the earth. While Gorgonopsids ruled the land with their saber teeth and advanced hunting strategies, another theater of predation was unfolding in the rivers, swamps, and wetlands that still persisted across the Permian landscape. The water has always been a dangerous place, a realm where visibility is limited, where escape routes are constrained, and where predators can lurk unseen beneath murky surfaces. In the Permian, these aquatic environments house some of the most formidable predators of the era. Massive reptiles, the made every river crossing a potentially fatal gamble. Step to the edge of a late Permian river, and you're entering a different world from the dry uplands where Gorgonopsids hunt. The air is thick with humidity, the banks lined with primitive conifers and seed ferns. The water moves slowly, dark and opaque, carrying sediment and organic matter that clouds visibility to mere inches. Something large disturbs the surface briefly, creating ripples that spread outward, and then stillness returns. But the stillness is deceptive. Beneath that calm surface, apex predators patrol their territories, and they've been doing so for millions of years. The crocodile lineage is ancient, far more ancient than most people realize. While modern crocodilians are often called living fossils, their ancestors were terrorizing Permian waterways long before dinosaurs existed. Creatures like the Proterosuchids represented early archosauromorphs, the lineage that would eventually give rise to crocodiles, dinosaurs, and birds. These were not yet true crocodilians, but they were already exploring the semi-aquatic predator niche with remarkable success. Imagine Proterosuchus, one of the earliest and most successful of these aquatic hunters. This creature measured up to 6 feet in length, with a long, narrow snout studded with sharp, conical teeth, perfect for catching fish and ambushing anything that ventured too close to the water's edge. The body was streamlined, the tail powerful and laterally compressed, providing thrust for rapid acceleration through water. The legs were strong enough for terrestrial movement but positioned and shaped for aquatic efficiency. Proterosuchus could swim swiftly through rivers and lakes, could haul itself onto riverbanks to bask or pursue prey, and could remain submerged for extended periods, waiting with the patience of a perfect predator. But the crocodile-like hunters weren't the only massive reptiles claiming the waterways. The Permian swamps were also home to enormous amphibians that had successfully resisted the march of reptilian dominance by retreating into fully aquatic lifestyles. Prionosuchus, which we mentioned earlier, deserves fuller attention here. This creature was a monster by any standard, potentially reaching lengths of 30 feet, making it the largest amphibian ever known to science. Think about that for a moment. An amphibian as long as a school bus, lurking in Permian rivers. Prionosuchus had a crocodile-like body plan, which is a testament to convergent evolution, the tendency of unrelated animals in similar environments to evolve similar solutions. The skull was long and flattened, filled with hundreds of small, sharp teeth ideal for catching fish and other aquatic prey. The body was elongated and powerful, the legs reduced to relatively small paddles that assisted in steering but weren't used for terrestrial locomotion. This was a creature that had committed fully to aquatic life, abandoning the land that its ants. Stores had worked so hard to colonize. The hunting strategy of these giant aquatic predators combined patience and explosive violence. Picture Prionosuchus lying on the bottom of a murky river, perfectly camouflaged against the sediment, barely moving except for the gentle undulation of its gills. A school of primitive fish swims overhead, unaware of the danger. The massive amphibian's eyes track the movement, calculating distance and trajectory. Then, with shocking suddenness, the creature surges upward, its powerful tail driving it through the water, jaws gaping wide. The fish scatter, but several disappear into that cavernous mouth, those hundreds of small teeth ensuring that nothing escapes once caught. But Prionosuchus didn't limit itself to fish. Anything crossing the river, any terrestrial animal coming to drink, any smaller amphibian or reptile venturing into the water, all were potential prey. The attack pattern would be familiar to anyone who's watched modern crocodiles hunt. The motionless waiting, the sudden explosion of movement, the powerful jaws clamping shut, and then the death roll, spinning in the water to disorient prey and tear away chunks of flesh. These hunting techniques were ancient even in the Permian, refined over millions of years of evolution. Other massive reptiles explored different aquatic niches. Some evolved into marine predators, venturing into the shallow seas that covered portions of the continents. These early marine reptiles were experimenting with body plans that would later be perfected by the ichthyosaurs and plesiosaurs of the Mesozoic. They developed streamlined bodies, paddle-like limbs, and hunting strategies adapted for open water rather than rivers and swamps. The waterways of the Permian were layered ecosystems where predators competed and coexisted in complex relationships. The riverbanks and shallows were dominated by creatures like Proterosuchus, which could operate in both water and on land. The deeper channels were the domain of fully aquatic giants, like Prionosuchus, and in the transitional zones, in the swamps and floodplains where water and land merged, a diverse assemblage of semi-aquatic creatures carved out their own niches. These aquatic predators also had to contend with the synapsid predators that controlled the land. A Gorgonopsid coming to the river to drink was too large and dangerous for most aquatic predators to attack, but nothing was truly safe. There are fossil sites showing evidence of interactions between terrestrial and aquatic predators, suggesting that the boundaries between these realms were contested, and that animals on both sides sometimes crossed into the other's territory with fatal results. The key to understanding these ancient aquatic ecosystems is recognizing that they represented a parallel evolutionary theater, one that was developing sophisticated predators simultaneously with the more famous terrestrial lineages, while synapsids were evolving saber-teeth and improved posture on land. Aquatic reptiles and amphibians were perfecting ambush hunting, hydrodynamic body shapes, and sensory systems adapted for murky water. Both groups were pushing the boundaries of what was possible, exploring the limits of size and predatory efficiency. These massive aquatic predators were the ancestors, both literal and spiritual, of later giants. The lineage that included Proterosuchus would eventually give rise to true crocodilians, which would persist through the age of dinosaurs and survive to the present day. The giant amphibians like Prionosuchus represented an evolutionary dead end, but they demonstrated that the amphibian body plan could be scaled up to truly massive sizes when freed from the constraints of terrestrial life. And millions of years later, In the Paleocene epoch following the extinction of the dinosaurs, a different kind of giant would emerge, Titanoboa. A snake 50 feet long that would rule South American rivers with the same dominance that Prionosuchus had exercised in the Permian. But all of this, the crocodile ancestors, the giant amphibians, the diverse assemblage of aquatic predators, all of it was about to face the same existential threat that menaced the terrestrial world. The great dying approached, and when it came, the rivers and swamps would offer no refuge from the catastrophe that would reshape life on Earth. For nearly 50 million years, the synapsids had ruled. Gorgonopsids prowled the uplands with their saber-toothed teeth gleaming. Massive dicynodonts grazed in herds across ancient plains. Giant amphibians and early archosaurs controlled the waterways. Life had diversified into countless forms, had filled every available niche, had created ecosystems of stunning complexity. The Permian world was thriving, teeming with bizarre and magnificent creatures that seemed destined to inherit the Earth's future. And then, 252 million years ago, the world ended. Not suddenly, not in a single catastrophic moment, but in a cascade of environmental catastrophes that unfolded over perhaps 60,000 years. Which sounds like a long time until you realize that in geological terms, 60,000 years is the blink of an eye, a heartbeat, a moment of planetary violence so intense that it nearly sterilized the entire surface of the Earth. This was the Permian-Triassic extinction event, known colloquially and appropriately as the Great Dying, the worst mass extinction in the history of complex life on our planet. The numbers are almost incomprehensible. 96% of all marine species went extinct. 96%. The oceans, which had been filled with diverse communities of trilobites, brachiopods, corals, and countless other organisms, were reduced to nearly lifeless wastelands. On land, approximately 70% of terrestrial vertebrate species disappeared. The forests died. The food chains collapsed. Entire ecosystems simply ceased to exist. For the only time in Earth's history, insects experienced mass extinction. Even the microbes in the soil were devastated. This was extinction on a scale that makes the death of the dinosaurs look like a minor inconvenience. What could cause such comprehensive destruction? What force could be powerful enough to bring life on Earth to its knees? The answer, as scientists have pieced it together from rocks and fossils and geochemical signatures, is that it wasn't one thing. It was everything. It was a perfect storm of planetary catastrophes, each one feeding into the others, creating cascading feedback loops that amplified the destruction beyond anything life had experienced before. The trigger, most scientists now believe, was volcanism, but not the kind you see in documentaries with a single mountain erupting. This was flood basalt volcanism on an almost unimaginable scale. In what is now Siberia, massive volcanic eruptions began, but these weren't explosive eruptions that hurled ash into the sky. These were fissure eruptions, cracks in the Earth's crust miles long, pouring out lava in quantities that defy comprehension. Over the course of perhaps 1 million years, these Siberian traps eruptions released enough lava to cover an area larger than Western Europe, in layers of basalt up to 2 miles thick. But the lava itself wasn't the killer. It was what came with it. The eruptions released staggering quantities of gases into the atmosphere: carbon dioxide, sulfur dioxide, and methane in volumes measured in gigatons. The sulfur dioxide created acid rain that fell across the entire planet, poisoning freshwater systems and acidifying soils. The carbon dioxide began warming the atmosphere, triggering a runaway greenhouse effect. Global temperatures soared, rising by perhaps 10 to 15 degrees Celsius. The polar ice caps melted. Sea levels rose and fell chaotically. As the oceans warmed, they began to lose their ability to hold dissolved oxygen. The cold, oxygen-rich waters that normally circulate from the poles to the equator slowed and stopped. The deep ocean became anoxic, devoid of oxygen, and in these conditions, bacteria that produce hydrogen sulfide began to thrive. Hydrogen sulfide is toxic to most life, and as these bacteria proliferated, they released their poison into the water and eventually into the atmosphere. The oceans themselves became toxic, and the smell of rotten eggs would have pervaded coastal areas worldwide. But wait, it gets worse. The warming temperatures destabilized methane hydrates, frozen deposits of methane trapped in ocean sediments and Arctic permafrost. As these deposits melted, they released massive quantities of methane into the atmosphere. Methane is a greenhouse gas far more potent than carbon dioxide. And this additional methane drove temperatures even higher, which released more methane, which increased temperatures further, a feedback loop spiraling out of control. The warming ocean water expanded, raising sea levels and flooding coastal areas. But simultaneously, the changed ocean chemistry meant that massive amounts of carbon dioxide were being released from the ocean into the atmosphere. The ocean acidified as carbonic acid formed from dissolved CO2, making it increasingly hostile to any organism with a calcium carbonate shell. The reefs died. The shelled organisms dissolved. The food chains that depended on them collapsed. On land, the story was equally apocalyptic. The forests, stressed by acid rain and rapidly changing climate, began to die. Without plant life to anchor the soil, erosion accelerated. Sediment choked the rivers and streams. The herbivores, losing their food sources, starved. The predators, losing their prey, followed them into extinction. The magnificent Gorgonopsids, the pinnacle of synapsid evolution, vanished. The diverse communities of Dicenodonts were reduced to a handful of species. The giant amphibians disappeared from the rivers. Some scientists believe the situation became even more extreme. There's evidence that oxygen levels in the atmosphere dropped significantly, perhaps falling to 15% or lower, making it difficult for large animals to breathe. The ozone layer may have been damaged by the volcanic gases, allowing harmful ultraviolet radiation to reach the surface and causing mutations and death in plants and animals alike. Wildfires raged across continents, turning dead forests into ash. For creatures trying to survive this apocalypse, there was no safe haven. The oceans were toxic and oxygen depleted. The land was scorched and barren. The air itself was poisoned. Animals that retreated to high altitudes found no refuge, as the changed atmospheric composition made breathing difficult. Those that sought shelter in burrows found soils contaminated with toxic compounds. Migration was pointless because the catastrophe was global, affecting every ecosystem on every continent simultaneously. The extinction didn't happen overnight, but in geological terms, it was rapid. Fossil records showed diverse, thriving communities in older rock layers, then a boundary layer marking the extinction event, and above that, rocks containing almost nothing. Just a few hardy survivors, generalist species that could tolerate the new, hellish conditions. The recovery would take millions of years. In the immediate aftermath, the Earth was almost unrecognizable. Ecosystems were reduced to their simplest forms. A single species of hardy plant might dominate vast areas. The few surviving animal species existed in low numbers, struggling to find enough food and suitable habitat. The complex food webs that had taken millions of years to evolve were gone, replaced by bare bones communities of desperate survivors. The Great Dying reset the evolutionary clock. The synapsids, which had dominated for so long, were reduced to a handful of lineages. The Gorgonopsids were completely extinct. Most of the diverse therapsid groups were gone, but a few survived, and from these survivors, mammals would eventually emerge. The archosaurs, which had been relatively minor players in the Permian, found opportunity in the devastation. They would diversify and eventually give rise to the dinosaurs. The Permian-Triassic extinction reminds us that our planet, for all its beauty and abundance, is capable of catastrophic violence. It shows us that even the most successful groups, even apex predators that have dominated for millions of years, can be swept away when planetary systems go haywire. The Great Dying was Earth's worst day. A near-death experience for life itself, and its scars are written in the rocks for anyone who knows how to read them. In the immediate aftermath of the Great Dying, Earth resembled a graveyard. The vibrant ecosystems that had flourished for millions of years were gone, replaced by desolate landscapes where only the hardiest organisms clung to survival. The air was still toxic, the ocean still lifeless in many regions, the soil contaminated and barren. If you could have stood on that post-apocalyptic planet 251 million years ago, you might have wondered if complex life would ever recover, if the Earth would forever remain this broken, simplified shadow of its former glory. But life is resilient. Life is opportunistic. Life finds a way. The survivors of the Permian-Triassic extinction were the generalists, the adaptable, the tough. Small body size helped, requiring fewer resources to survive. The ability to burrow provided protection from temperature extremes and radiation. Omnivorous diets meant flexibility when specific food sources disappeared. The creatures that made it through the bottleneck weren't necessarily the strongest or the fastest or the most impressive. They were simply the ones whose particular combination of traits happened to match the new harsh reality. Among the synapsid survivors were a group called the cynodonts, small to medium-sized therapsids that would eventually give rise to mammals. They were unimpressive creatures by Permian standards, nothing like the magnificent Gorgonopsids that had preceded them. But they had the right adaptations, efficient metabolism, the ability to dig burrows, opportunistic feeding habits. In the wasteland of the early Triassic, these qualities were worth more than saber teeth or massive size. But the real winners of the extinction, the group that would seize the opportunity created by catastrophe and transform it into unprecedented success, were the archosaurs. These reptiles had been minor players in the Permian world, overshadowed by the dominant synapsids, but they possessed certain advantages that would prove crucial in the recovery period. Their metabolism was efficient, their body plans flexible, and they had already developed some degree of temperature regulation. When the world was reset, when the ecological playing field was leveled and the old dominant groups were decimated, the archosaurs were positioned to exploit the vacuum. The early Triassic period was a time of experimentation and recovery. For millions of years, ecosystems remained simple, dominated by just a few species. Lystrosaurus, a pig-sized dicynodont, became perhaps the most common land vertebrate on Earth, its fossils making up as much as 95% of all terrestrial vertebrate fossils from the early Triassic. Imagine that, a world so depleted of diversity that a single species dominated entire continents. This was the blank canvas, the empty world waiting to be repopulated, and slowly, incrementally, the archosaurs began to diversify. They split into two major lineages. One branch would lead to the crocodilians, exploring semi-aquatic predatory niches similar to those their ancestors had occupied in the Permian. The other branch, the avametatarsalia, began experimenting with increasingly upright postures, longer legs, and more active lifestyles. These creatures were becoming specialized for life on land, for running and hunting and competing in terrestrial ecosystems. By the Middle Triassic, approximately 240 million years ago, the archosaurs had produced a diverse array of forms. There were massive herbivores, swift predators, armored browsers, and everything in between. Some grew to impressive sizes, reclaiming the ecological roles that giant synapsids had once filled. The world was recovering, filling up with life again, though it looked very different from the Permian world that had been lost. And then, in the late Triassic, approximately 230 million years ago, something remarkable happened. A new group emerged from within the archosaur lineage, creatures with a revolutionary body plan. They stood fully upright, their legs positioned directly beneath their bodies, rather than splaying out to the sides. This posture was extraordinarily efficient, allowing for sustained running, reduced energy expenditure, and improved breathing during locomotion. They developed hollow bones that reduced weight without sacrificing strength. Their respiratory systems became incredibly efficient, possibly including air sacs similar to those in modern birds. These were the first dinosaurs, and they were small, unimpressive creatures at first, no larger than dogs, running through the forests and scrublands of the late Triassic. Creatures like Eoraptor and Herrerasaurus didn't look like world conquerors. They looked like minor predators, hunting small prey, competing with other archosaurs and the surviving synapsids. But they carried within them the seeds of future dominance. The dinosaurs had evolved at exactly the right time. The world had recovered enough from the Permian extinction to support complex ecosystems again, but it was still malleable, still open to new forms and strategies. The old Permian giants were long gone. The Gorgonopsids, with their saber teeth, the massive dicynodonts, the diverse assemblage of therapsids, All had been erased by the jar. Eat dying. The ecological niches they had occupied were available, waiting to be claimed by whatever group could adapt to fill them. Another extinction event at the end of the Triassic period, smaller than the Great Dying but still significant, eliminated many of the archosaurs that had been competing with dinosaurs. This Triassic-Jurassic extinction, possibly caused by more volcanic activity and climate change, removed many of the obstacles standing between dinosaurs and dominance. When the Jurassic period began 201 million years ago, the dinosaurs were positioned to inherit the Earth, and inherit it they did. Over the next 135 million years, dinosaurs would diversify into the most spectacular array of terrestrial animals the planet has ever seen. From the massive sauropods that weighed as much as 10 elephants, their long necks reaching into the treetops, to the swift, intelligent raptors that hunted in coordinated packs. From the armored ankylosaurs built like living tanks to the tyrannosaurs with their bone-crushing bites, dinosaurs explored every conceivable ecological niche and body plan. They evolved flight, giving rise to birds, which are the only dinosaurs still with us today. They developed complex social behaviors, sophisticated parenting strategies, elaborate display structures. They dominated every continent, thrived in environments from polar forests to tropical swamps to arid deserts. The age of dinosaurs lasted longer and the age of synapsids, longer than the age of mammals has lasted so far. It was one of evolution's greatest success stories. But here's the profound truth that we must grasp. None of it would have been possible without the Great Dying. The dinosaurs rose to dominance not because they outcompeted the Permian giants, not because they were inherently superior. They rose because those giants had been swept away by catastrophe, because the extinction had created space, had opened opportunities, had reset the game. The Gorgonopsids, the sailback synapsids, the giant amphibians, the bizarre creatures of the Carboniferous and Permian. These weren't evolutionary failures. They were victims of planetary violence, casualties of environmental catastrophe. They had ruled their world successfully for tens of millions of years. But when the Earth's systems went haywire, when the volcanoes erupted and the oceans acidified and the temperatures soared, even the most successful groups could not survive. Their extinction was the dinosaurs' opportunity. The death of one world enabled the birth of another. This is the pattern of life on Earth, written again and again in the fossil record. Catastrophe and renewal, extinction and diversification, death and rebirth. The giants that time forgot had to die, had to be swept away, so that new giants could rise in their place. And when we look at the world today, when we see the dominance of mammals, the diversity of birds, the complexity of modern ecosystems, we're looking at another chapter in the same story. The dinosaurs ruled for 130 to 5 million years, and then an asteroid struck, and the age of mammals began. What came before made possible what came after. The past feeds the future, and extinction, terrible as it is, opens doors that otherwise would never exist. The pre-dinosaur world. That strange realm of scaled trees and giant insects, of saber-toothed synapsids and sailed predators, of massive amphibians and revolutionary eggs. That world is gone and will never return. but it laid the foundation for everything that followed. The dinosaurs inherited a world reshaped by catastrophe, and they made it magnificent. The story of life before dinosaurs is ultimately a story about opportunity, about resilience, about the unstoppable creativity of evolution when given space to work. It's a reminder that what seems like an ending is often just a beginning in disguise. The dinosaurs we know and love were just one chapter in Earth's epic story. But before them came an era of giants so strange, so magnificent, that they seem like science fiction. These creatures didn't just exist, they dominated their world completely, until the planet itself hit the reset button. Next time you see a dragonfly or a millipede, remember, you're looking at the descendants of giants, the survivors of an age when Earth experimented with life on a scale we can barely imagine. If this journey through deep time amazed you, subscribe and join us as we uncover more incredible stories buried in Earth's past. What should we explore next? Let me know in the comments below.